Ladies and gentlemen, let us begin. Well, distinguished guests and ladies and gentlemen, welcome to the Asian Science Camp 2022, the so-called the Asian Leo meeting with me, Shin Ji-hye, as your MC. Well, it's an honor to serve today as the MC at this precious gathering. This year, because of the ongoing pandemic, we are hosting the Asian Science Camp in a hybrid style, which means that we're welcoming all the guests to join us, both on and offline. The offline participants are here with us at the ISB Science and Culture Center in Daejeon, and all the online participants are joining us through the official YouTube channel of IBS and also through Zoom. So thank you everyone for sparing your time to be here with us today. Before we begin, I would like to first call upon some of our precious supporters of ISC to stand and be recognized of their presence. As I call upon their name, please give them, each one of them, a big round of applause. First of all, here with us, we have President No Do-young of Institute for Basic Science. Welcome. And today, we also have Director Lee Chang-yoon of Ministry of Science and ICT of Republic of Korea. And we also have three distinguished guests from the International Committee. We have Chairman Milan Sanyal and IC members Zubi Paltiel and Lee Hyun-sul. Let us have all three be recognized for their presence. Yes, Chairperson Milan Sanyal is currently joining us through Zoom, so another personal welcome. And also we have Director Kim Eun-jun and Han In-sik from IBS. Welcome. And now for all of our online and offline participants, please give another big round of applause. Yes, thank you very much. The big applauses brings a lot of energy in this room. And before we dive in deep to our program, I would like to first introduce to you our host of Asia Science Camp 2022. So let us watch a clip on the IBS, the Institute for Basic Science, through the screen.
인류가 오랜 시간 되물어왔던 가장 근본적이고 거대한 질문들에 답하려는 노력. 기초과학, 작은 호기심에서 시작된 새로운 발견. 인류의 삶을 윤택하게 하고 역사 발전을 이끄는 원동력이 됩니다. 그리고 여기 끊임없이 질문한 인류사 위대한 과학자들처럼 거대한 질문을 던지는 사람들이 있습니다.
우리 우주는 어떻게 탄생됐으며 그것을 밝혀줄 궁극의 자연법칙은 무엇일까요?
우주는 무엇으로 이루어져 있을까?
Can we build and control structures one atom at a time?
나노 소재가 우리 실생활에 어떻게 도움을 줄 수 있을까요?
세포의 운명은 어떻게 결정될까?
유전자를 교정해서 난치병을 치료할 수 있을까?
인간의 뇌는 어떻게 작용할까요?
바이러스 연구를 통해 인류는 바이러스성 질병을 극복해낼 수 있을까? 지구는 어떻게 변화할까? 과거와 미래의 기후는 인류에게 어떤 영향을 줄까? 우주, 물질, 생명. 우리 세계를 이루는 모든 존재의 본질을 탐구하고 더 나은 미래를 향해 질문하는 사람들. 우리는 기초과학연구원입니다. 기초과학연구원은 대한민국의 눈부신 성장을 상징하는 93년 대전 엑스포의 역사적 현장에 자리했습니다.
기초과학연구원은 세계 최고 수준의 기초과학 연구를 수행하는 국가연구기관입니다. 우리는 우수한 연구자들의 자율적이고 개방적인 연구가 새로운 발견으로 이루어진다고 믿습니다. IBS는 세계적인 수월성을 가진 연구자를 엄격히 평가하여 연구단장으로 선정하고 이들이 연구할 수 있는 최고의 환경을 제공합니다. IBS는 국가적 차원의 장기, 집단, 대형 기초과학을 지향합니다. 거대한 우주로부터 눈에 보이지 않는 미시 세계까지 관찰할 수 있는 연구시설도 필요합니다. IBS의 암흑물질 실험시설, 초강력 레이저 시설, 그리고 구축 중에 있는 중용 가속기 등은 세계에서 손꼽히는 수준의 연구시설입니다.
기초과학연구원은 과학도시 대전의 중심에 위치한 도시명 연구기관입니다. 대전 도룡동에 위치한 본원뿐만 아니라 서울, 수원, 부산, 대전, 대구, 광주, 포항, 울산 등 전국에 31개 연구단을 운영하고 있습니다. 서울대, 카이스트 등 전국의 우수한 대학과 인프라와 인력을 공유하며 협업하고 차세대 기초과학 연구 리더를 육성하고 있습니다. 우리의 환경과 미래를 잇는 기초과학은 오늘도 빠르게 성장하고 있습니다. 기초과학은 우주에서 인간에 이르는 모든 것에 대한 탐사입니다. 왜라는 순수한 호기심이 수많은 생명을 살리고 인류의 삶에 기여한 것처럼 기초과학은 지금껏 경험해보지 못했던 새로운 세상으로 인류를 인도할 것입니다. 작은 호기심이 가져올 무한한 가능성을 위하여 우리의 질문은 계속됩니다. 기초과학연구원
Yes, through the clip, we were able to learn more about the IBS, which is conducting world-leading researches. In order to show our appreciation to our host of ASC, please give another big round of applause. Yes. Yes, hoping you will have a wonderful week. Yes, I can see that you're ready to bring your applauses together. So why don't we give a big applauses to our organizers as well. So we have introduced to you our hosts and organizers. Well, as you can see, we are celebrating 14th anniversary this year, and we have taken a special care in coming up with the lineup of speakers. And as we have seen a brief introduction of ASC, now we're going to welcome the chairman, Milan Sanyal of International Committee, who is joining us online to give us more details of ASC program. Well, sir, hello, are you there?
Yeah, I'm there.
Okay, since we can hear you clearly, please please start your presentation. Thank you.
How do I share my screen?
Yes, I think at the downside of your screen, you will see an icon that says maybe share the screen.
You have my file already with you, I guess.
I will see if the organizers can do the file sharing. 네, 혹시 주최 측에서 파일 공유를 해주실 수가 있을까요? I think that's not ready yet, so would it be possible for you to share the slides with us?
I think it's not allowing me to share. If I
Do you not see the share slides icon?
No, I'm seeing only.
Yes, I think it's in the settings banner, perhaps. Yes, these are some of the perks of having, internet connection and having to connect with other people online. Well, I think some of our staff has want to grab the files as well. So until then, why don't we have some small talks together? Or would you?
Okay. Or I can make the presentation without slides if the slides are problem.
Yes, perhaps we can do that as well. So would you first maybe introduce yourself and a brief about the AESC program, and we'll try to get the files.
Okay, first of all, I'm extremely happy, and on behalf of international committee members, it's my pleasure to congratulate South Korea for organizing this event after 2 years of null period. Although it is a hybrid meeting, but it's a fantastic beginning. And we are all hoping that the young generation will get their inspiration from this meeting. And that's the main purpose of Asia Science Camp, to pass on the knowledge and information and inspiration from our generation to the next generation, so that our human nature and our adventure to future remains intact and progress well. I'm very sorry that I'm not able to present the file, but I thought I already sent my file to the organizer. It will be better if it can be displayed. Otherwise, I'll just continue and tell from the slides what I want to present. We human, we know how to survive such catastrophes which we have just now gone through. And it's not the first time. At least the last one we remember happened in 1918 through Spanish flu. And over 3 waves of infection, we lost 50 million people. And even this time, for this COVID-19, we have already lost several million over the world through this infection. But the humans know how to survive through this, and humans know how to look for future. And Asia Science Camp is one such example. In spite of all this problem, South Korea has organized this event where more than 100 people are already present physically. I'm feeling bad that I'm not present physically there, but I can see how excited you are. But remember, 1918 didn't stop the human society to innovate. As it is obvious, from the next 50 years, we discovered fantastic sciences. I shall show some of the chosen list of Nobel Prizes which happened, and for example, in 1918 itself, we had fantastic Nobel Prize in Max Planck in recognition of services he rendered to the advancement of physics by his discovery of energy quanta. Max Planck changed the way physics is done in 1918 itself, when we have gone through this Spanish flu. Next, I would like to mention is, of course, Albert Einstein. We discovered Einstein not only for his services to theoretical physics, and especially for his discovery of the law of photoelectric effect. We all know that after that, Einstein discovered so many things. The papers he published in a couple of years, probably each of them could have won a Nobel Prize. So I think Einstein himself is the discovery of humankind in how the intellect can change the world. After that, in 1922, the Nobel Prize in Physics went to Niels Bohr. He's another man who changed our thinking of structure of atoms for his services in the investigation of structure of atoms and of the radiation emanating from them. It's not only physics, that at that time, as I said, that since the Spanish flu, so many new discoveries happened which changed our understanding of the world and science. For example, in 1923, the Medicine Nobel Prize went to Frederick Banting and John MacLeod.
Sir, I'm sorry to interrupt, but if you could tell us which slide you're in, the number, then we will have the slides put up.
Okay, I'm in number 3 now.
3, okay. Now I think you will be able to see the slides as well. So as the slides are ready, let's resume with your presentation.
Okay, but maybe I will not be able to see, but I can see my slides here, so I will continue, okay? Maybe it is visible to the audience, so it will be very nice.
Yes, thank you.
Well, as I was telling, that the discovery of insulin changed the way we understand the human health and how to treat it. After that discovery, so many other things happened, and it's remarkable that within few years of Spanish flu, so many discovery was happening. The next one I would like to mention is 1930 Medicine Nobel Prize. It's Karl Landsteiner for his discovery of human blood groups. Now it is the young, my young friends will realize that, remember, the blood groups were discovered only in 1930, and how we have learned so much about the human health since then. Of course, I would like to mention our own Indian example of Venkata Raman sir, for his Raman effect. This was a physics Nobel Prize in 1930, and it's a fantastic work which can be done with a very simple instrument that he has shown. And then, of course, we continued, and there were so many Nobel Prizes. I will not go through all the details, as you can see on the screen. And now the question is, what is expected in the next 50 years from today, and how do we do that? How do we make sure that such fantastic discoveries will happen in future? The only way we can make sure that such fantastic discoveries will happen in next 50 years is to inspire and train our next generation. And that's the main purpose of this Asia Science Camp. We have to make sure that the world is free of boundaries as far as knowledge and the discoveries are concerned, and we can provide an open world to our next generation, these fantastic students who have gathered today in this ASC hall, and we look forward in the next 5 days all their involvement and mixing with the Nobel laureates who have agreed to give their presentation, and also the frontline researcher. Now, what is the future world we envisage? And that is, I will quote from Tagore, a famous poet from India. Actually, he was the first Asian Nobel laureate. In literature, he got his Nobel Prize in 1913. In his own handwriting, as you can see on the screen, he thought about a world which will allow people to discover new things. So I just quote, where the mind is without fear and the head is held high, where knowledge is free, where the world has not been frittered in fragments by narrow domestic walls, where words come out of deep of truth, there awaken my country into that heaven of freedom, my father. That's the thing he imagined, and I think that should be the motto of our Asian Science Camp, so that we give such kind of environment to our next generation to proceed further and discover fantastic science in next 50 years. Thank you very much for your attention. Thank you.
Yes, thank you very much, Chairperson, for your introduction today of the program. We'll be looking forward to the day we meet again in person. Thank you. Please give him another big round of applause. And now moving on, we have President No Do-young of IBS who will deliver the welcome speech and the opening speech together. Please, ladies and gentlemen, give him a big round of applause.
Good morning, everyone. Good morning. My name is Do-young No, as I was introduced, and I'm the president of Institute for Basic Science in Korea. It's my honor to welcome you all to the 2022 Asian Science Camp. This is the 14th camp, which was postponed for 2 years due to the pandemic, and we are still suffering from the pandemic. And so even now, many student delegates are participating in online, and we saw our chairman participating online. Today we have about 200 students participating from 24 countries. So this is a truly global event. I thank you, Dr. Jubi Patel, participating in person during this difficult time. I remember Chairman Milan Sanyal, and he may remember me. He's a few years ahead of me, and we were working together at the Brookhaven National Laboratory in United States, which was late 1980s. So that I was happy to see him even on a screen today. This is the second Asian Science Camp held in Korea. And the first one was held at KAIST, which is just down the road from here, a few months ahead of the establishment of our institute, Institute for Basic Science, known as IBS. As you saw from introduction video, IBS is the Korea's first dedicated basic science research institute, which focuses on long-term research that requires large groups of people. IBS is currently operating 33 centers, and many of the directors of our centers will present a lecture at this camp. We are covering the basic science research field from mathematics, physics, chemistry, biology, and earth science, and interdisciplinary area. Centers are located at this headquarters at IBS, and many research-oriented institutes and schools around Korea. That include KAIST, POSTECH, and Seoul National University. Today's Asian Science Camp roots back to the Lindau Nobel Laureate meetings, which started about 70 years ago. And the purpose of Lindau's meeting was for leading scientists to meet with young scientists to encourage, to mentor, and to pass on the scientific flame. Facilitating the transfer of the knowledge from one generation to the next, and also from scientists to the public, is very critical. This is national behind this year's slogan, Science for Humanity and Society. This annually held Asian Science Camp was modeled after this Lindau's meeting, and which focuses on Asia. This is why you are here today. Your generation will become the leader of next generation in science, and we cannot emphasize that enough. This camp is to help you to prepare for the future. We have an exciting week planned for you. Many leading researchers, as you saw in the video clip, including the Nobel laureate, are here to provide stimulating lectures and participate in parallel panel discussions. Poster presentations and social activities and tours are also prepared. I do recommend you to actively participate in the lectures and event which is outside of your major. Since the world is changing so rapidly and this interdisciplinary research is so critical in the future. The knowledge you gain, even from seemingly unrelated subject, will only help you in your career as a future science researchers. So again, I would like to welcome everybody to Asian Science Camp 2022, to Korea, and to IBS. We are all excited that you are here and hope you have a wonderful week this week and a very fruitful week. Thank you very much. Thank you.
Thank you very much, President, for emphasizing the importance of this Asia Science Camp. And as he have mentioned, this camp is indeed important for us to pave the way towards the future. And now moving on, we will hear a congratulatory speech from Director Lee Chang-yoon of Ministry of Science and ICT. Please welcome him with a big round of applause.
여러분 반갑습니다. 저는 과학기술정보통신부에서 기초원천연구정책관으로 있는 이창윤입니다. Good morning, everybody. My name is Lee from the Ministry of Science and ICT. I'm responsible for the promotion of the basic science and the fundamental technology in my ministry. Unfortunately, today I prepared my remarks in Korean. So from now on, I'd like to ask somebody in this room to help me to translate what I'm saying into. Okay. 네, 먼저 2022년 아시안 사이언스 캠프 개최를 축하드립니다.
Well, first of all, I would like to congratulate on the opening of Asia Science Camp 2022.
오늘 행사 개최를 위해서 노력해 주신 조직위원회 밀란 살란 박사님하고 기초과학연구원 노도영 원장님께 감사 말씀드립니다.
I would like to first express my gratitude to Chairperson Milan Salam and President No Do-young of Institute for Basic Science for all the efforts put to host this event.
아울러서 이번 일주간 강연해 주실 세계 저명한 과학자분들과 또 아시아 각국에서 참석해 주신 우리 미래의 주역, 미래 훌륭한 과학자가 되실 우리 청년들 같이 할 수 있게 돼서 너무나 반갑습니다.
And I'm glad that I am joined by the world-renowned scientists as well as the Asian youth who are the leaders of the future.
If If I have seen father, it is by standing on the shoulders of the giant. 이 문장은 뉴턴이 17세기 중반에 그의 경쟁자이죠. 로버트 훅에게 보낸 편지에 나오는 문장입니다.
The quote that I have just read is from a letter that has been sent to the rival Robert Hu.
아마도 그 당시에는 이제 같은 학문을 하시는 분들끼리 편지를 주고받으면서 이론에 대해서 비판을 하거나 논쟁을 하는 부분들이 많이 있었던 것 같습니다.
I think by that time there was a culture of receive and giving letters through the comments of their researchers.
이 문장에서 뉴턴이 말하고자 했었던 거는 본인의 과학적인 발견이 그의 선배 과학자인 코페르니쿠스나 갈릴레이나 케플러 이런 분들의 과학적인 성과에 기반해서 나왔다라는 것을 겸손하게 지적하고 있는 내용입니다.
What I think Newton was trying to say was that his scientific researches or foundings was based on his former researchers' founding, such as the Kepler or Cobelier or Galileo's foundings.
저는 이러한 뉴턴의 말이 오늘부터 일주일 동안 개최되는 아시안 사이언스 캠프의 의미와 취지를 너무나 잘 설명해주고 있다라고 생각을 합니다.
And I think this quote that I have read from Newton exactly explains the meaning of ASC.
우리 젊은 청년들이 세계 각국의 저명한 과학자들과 충분한 깊이 있는 대화를 통해서 미래의 과학자로 성장해 나가는 시간이 될 것이라고 확신합니다.
I am confident that this camp will serve as a platform for all the Asian youth to have deep conversation with the world-renowned scientists and to become future scientists.
존경하는 과학자 그리고 아시아를 대표하는 청년 여러분, 올해는 유엔이 지정한 세계 기초과학의 해이기도 합니다.
Respected scientists and youth representing Asia, this year has been designated as the International Year of Basic Science by United Nations.
기초연구는 사물의 근본적 이해를 통해서 사고방식의 틀을 전환하고 새로운 시대를 여는 역할을 할 뿐만 아니라 공학과 응용과학 혁신의 밑바탕이 되기도 합니다.
Well, basic research not only plays a role in opening a new era through transforming the framework of thinking about the fundamental understanding of things, but also is a stepping stone for engineering and applied science innovation.
지금까지 그래왔듯이 앞으로도 기초과학에 대한 연구는 자연 현상의 원리를 규명해내고 오늘날 세계가 당면한 감염병이나 기후위기 등 여러 가지 문제들을 해결할 수 있는 근본적인 토대를 마련할 것입니다.
As it has done until now, the basic science research will continue to understand the principle of natural phenomena, and it will lay the foundation for solving various problems such as the infectious diseases and climate crisis facing the world today.
저는 한국을 비롯한 세계 각국의 정부가 우리 젊은 연구자들이 창의적이고 도전적인 연구를 마음껏 할 수 있도록 지원을 아끼지 말아야 한다고 생각합니다.
I believe for all the researchers to freely implement their researches, we need the support from the government.
오늘 참석하신 미래의 청년 과학자 중에서 누군가는 우주 탄생의 비밀을 풀 것이고요. 또 다른 누군가는 기후변화나 감염병에 대응한 과학적 대응 방안을 연구하는 도전을 하시게 될 것이라고 생각합니다.
And some of you here will be solving the birth of the planet, and some of you might also find the answers for scientific measurements of solving the pandemic.
저는 여러분의 도전이 충분히 실현될 수 있기를 응원합니다.
And I'll be cheering for you and rooting for your challenges to be realized.
오늘 이 자리가 향후 아시아를 넘어서 세계적인 기초 연구 발전을 이뤄내는 중요한 시간이 되었다라고 기억되기를 기대하겠습니다.
And I'll be looking forward for all of you to remember today as a stepping stone of going beyond Asia and going to the world stage.
감사합니다. 좋은 한 주 맞이하십시오.
Thank you very much for listening, and I hope you have a great week. Yes, thank you very much, Director Lee, for the speech and for saying that the Ministry of Science and ICT will be always supporting our young leaders, the future scientists. And as I have mentioned, this program this year, because of the pandemic, is being held in a hybrid style. In online and offline, we're joined by many participants. Currently, through Zoom, we have more than 100 participants joining us today. So I would like to show them their faces. So if you can, would you please wave your hands and say hello? The participants in Zoom? Yes. Hello. Yes, this would be maybe a great chance for us to interact with each other. I can see there are a lot of people from the Indonesia, Philippines, Thailand. They're all the future leaders of the scientific world, just like our offline participants. For all of us, why don't we set a big round of applause? Yes, thank you very much for joining us today once again. And now, there were lots of dignitaries who would love to join us here in person, but was not able to be here, but have sent a congratulatory message through the video. So let us take a look of them through the screen.
국회의원 이상민입니다. 우선 아시안 사이언스 캠프 2022 개회를 축하드립니다. 준비하신 모든 분들의 노고에 깊이 감사를 드립니다. ASC는 과학기술에 관심과 재능을 가진 청소년 그리고 청년들과 과학기술에 있어서 세계적 석학들과의 만남과 토론의 장을 제공함으로써 과학기술 우수 인재를 육성하고자 하는데 2007년 이후 줄곧 시행해 오고 있습니다. 이번 ASC 2022는 세계적 기초과학의 허브로 발돋움하고 있는 이곳 IBS에서 개최되는 것은 더욱 뜻깊다 할 것입니다. 인류가 맞닥뜨리고 있는 바이러스, 에너지, 기후변화 등 위기와 도전적 상황을 극복하고 인류 문명을 개척하고 진화 발전하기 위해서는 전 인류적 연대와 공조가 필수적입니다. 특히 과학기술인들이 집단지성과 공동 노력이 더욱 요구된다 할 것입니다. 그런 차원에서 ASC의 의미와 역할은 더욱 기대됩니다. ASC를 통해서 우리 젊은이들이 과학기술의 관심과 역량을 고도화하고 심화시키며 확산하는 좋은 기회가 될 것으로 믿습니다. 이번에 온라인과 오프라인으로 참여하는 25개국 250명의 과학계의 석학과 젊은이들이 꿈과 비전을 공유하고 그 실현을 위하여 함께 노력하기를 기원합니다. 저도 국회 차원에서 여러분들의 뜻과 노력에 응원을 보내며 적극 지원하도록 하겠습니다. 참여하신 모든 분들의 건강과 행운을 기원합니다. 감사합니다.
Dear members of the Asian Science Camp 2022, it is for me a great honor to open this science camp for two reasons. The first is because I like very much its basic philosophy, directly inspired from the famous Lindau meetings, which brings together Nobel Prizes and added to learn enthusiastic students, where we talk about the most advanced topics in a very relaxed and friendly atmosphere. The second reason is because I have a lot of respect for Korean science and scientists. I have been particularly involved with one of the top IBS infrastructure, the Gwangju Institute Science Center for Relativistic Laser Science, funded by one of your top scientists, Professor Chang-Yi Nam. I contributed to its inceptions of this center, and for about 10 years, I was a member of the science board. So I really learned to appreciate science and scientists. For me, the Asian Science Camp is a mirror of what's going on in Korean science today. So I will stop here and let you enjoy the rest of the workshop. Thank you to have me and to give me the opportunity to be with you for a very brief moment. Thank you very much.
Hello everyone, my name is Stefan Hell. I'm a physicist at the Max Planck Institute in Göttingen and Heidelberg in Germany, specializing in molecule scale resolution in fluorescence microscopy, a very exciting research field which most scientists thought that it would never come into being. I feel very honored that I was invited to give a presentation at the Asian Science Camp 2022 in South Korea. I think the mission of the Science Camp is more important than ever these days, promoting exchange between young scientists across all nations and nurturing friendships among scientists from all disciplines and backgrounds. After all, we live on the same planet, and as this pandemic has vividly demonstrated, we all face the same problems on this planet. Therefore, I wish you a very exciting gathering and all the best for all your future endeavors. Keep up your passion for science and keep up your positive outlook on the future.
Thank you very much for sending all of your warm remarks through the video. We will be looking forward to the day where the ASC will be held with all the participants in one room together. Well, having heard all the warm remarks, we're going to end the opening ceremony here. Thank you very much for the online participants and the offline participants for joining our opening ceremony today. So until now, I was your MC, Shin Jie. Thank you very much. And now I would like to welcome all of the offline participants to join me on stage for a commemorative photo together. Since this is a rare occasion, I would like to welcome all the participants to join me on the stage for the photo. Yes, please join me on the stage. ASC is an annual event that aims to enlighten the science talents, youth, through discussions and dialogues with scholars and also technologists in the world. Well, we will be with you throughout the week, and I hope that you will have a wonderful time here with us at ASC 2022 in Daejeon IBS Center. So please join us all on stage, and now we're going to have the photo together. We would like to ask the distinguished guests to join us at the first row, and the others will get in line. Please make sure that your faces are seen by standing in between the participants. Yes, we are quite a large group. Yes, maybe sitting at the first row would be great. That would be a great idea. And we can have participants at the second and the third row as well. The second row can maybe bend a knee a bit. Yes, the second row can bend the knee a little bit so that the others can be seen at the back. And I have forgot to mention that also from the Parliament of National Assembly, the national lawmaker Cho Seung-lee have also sent a congratulatory message for all of our participants. So another thanks goes to the lawmaker. And now, please make sure that all of your faces are seen. So at the corner, could you squeeze a little bit more to the center? Thank you. Let us see if all can be seen at one photo. Okay. Say ASC. Yes, now let us put our right fist up, showing our support towards the ASC. When I say science for humanity and society, please shout out ASC together. Okay? I will be looking forward to a big united voice. So, science for humanity and society. Thank you very much. This will be all for the opening ceremony. Thank you very much for your cooperation, and we'll be taking a break from now and resume for the lecture number 1. Thank you very much for your cooperation. Yes, as we are about to begin, participants, if you're still outside, would you please promptly enter the hall and be seated? We are about to begin our lecture for day 1 here at the camp. So, may I ask all the participants to now take their seats and be ready for all of our lectures. If you're still outside, please come in as we are ready to begin. Thank you very much. Yes, welcome back everyone. And now we're going to start our lectures for the day. We have for the lecture 1, the director Axel Timmermann of IBS Center for Climate Physics, who is going to touch upon the topic of humans and climate. So let us welcome him through the screen with a big round of applause.
Thank you very much for the introduction, and thank you all for joining the Asia Science Camp. I would like to share with you some ideas today about how humans have adjusted and adapted to climate change and how we are also changing, of course, our climate system. So this is going to be a perspective on our past, present, and future. And so first, I think it's important just to clarify the difference between weather and climate, because sometimes there are some confusions about these two terms. Of course, we know the weather characterizes the condition of the atmosphere over relatively short periods of time, let's say from hours to days, maybe weeks. We have a weather forecast, we don't have a climate forecast on TV. Weather includes extreme events, includes, for example, heat waves that currently Europe is experiencing, tropical cyclones, snowstorms, etc. However, climate characterizes much more the average weather conditions in a region over many, many years. For instance, the El Nino phenomenon, which influences climate in the tropics dramatically on interannual timescales, is a climate phenomenon. It's not a weather phenomenon. However, this climate feature can also influence weather, the statistics of weather systems. For example, global warming is a weather phenomenon. However, again, the weather is a climate phenomenon. However, the climate phenomenon itself can change the statistics, the occurrence of extreme weather events. And of course, ice ages, we will talk about them today, are also a climate phenomenon. So we have a clear separation between the two different timescales. Everything short is weather, everything long, when we talk about the average weather conditions, is the climate. Okay, let's talk about the past and how our human species has evolved in changing climate conditions. Well, this is the tree, essentially, of our human ancestors, and it goes back about 6 million years ago, and you can see some of these very early human groups or predecessors of our human species, Ardipithecus, Australopithecus, Paranthropus. These were essentially experiments of Mother Nature that didn't really work out. These are essentially twigs on this branch of human life that were not successful. So they disappeared, they became extinct. And then around 2 million years ago, really our genus Homo emerged from this relatively complicated tree. And we started probably in the savannas of southern and eastern Africa. And this is at a time when the climate also changed, and we'll come back to that. Then from these very early human ancestors, there were many different cousins, many different twigs that emerged from this large tree. The important one, very successful one, was Homo erectus. We will talk about this species later on. Homo heidelbergensis, Homo neanderthalensis, also known as the Neanderthals. And of course, we are currently the only survivor on this tree, this phylogenetic tree, the Homo sapiens. And we emerged around 300,000 years to 200,000 years ago, also in southern and eastern Africa. Okay, so we can ask the question, if the climate changed during this time period, did actually climate play a role in our evolution? And first I wanted to give you an idea of how climate changed and also why. What you're seeing here is a movie of the vegetation conditions over the last 1 million years. And what you can see is each color here corresponds to a different vegetation type. You can find tropical savanna here, for instance, tropical rainforest, there is desert, and so on and so forth. So you can see essentially the vegetation on our planet as it changed over time. And Ka refers to kilo years before present. So 400 Ka means 400,000 years ago. And what you can see are every once in a while you have these large ice sheets that form over North America and Eurasia. And these ice sheets, as they wax and wane, they characterize the typical glacial cycles, the ice ages that we know of. And over the last 1 million years, our climate system has been 80% in a glacial state, and the interglacial, the warmer state, is actually relatively rare. Okay, what you saw are these massive shifts, not only of the ice ages. I can rerun it maybe once more, but you can see that all of the vegetation patterns, they shift in time. And you can imagine, because humans and also animals, they are looking for food, they would also
Director Axel?
Yes?
Could you also move the slides as well? Because we are not able to control it from this side. So would you kindly turn it to the next page or so that the students can follow your presentation?
I'm doing it. I showed all the slides before.
Yeah, we were only able to see the first slide.
Really? How about now?
Now we can see the slide that you're showing. Yes, thank you.
I'm sorry.
Would you please maybe check, maybe press the space button one or so to see if the slides are moving? No, it's still. It's frozen.
Okay, let me do, I'm sorry about that. We just tested it and it went well. I do screen share once more.
Yeah, or maybe we should not put it in full mode, but maybe this would be much better rather than playing the slides.
Let's see once more. Can you see the shift?
No, it's frozen. Yeah, let's just leave it this way.
Okay.
Yeah, I think this would be better.
Okay, well, anyways, we just tested it. It worked fine. Okay, I'm sorry about that. So what you saw were large-scale, what we are supposed to see were large-scale shifts in the climate system. And there was a movie showing the vegetation patterns, how they changed over the last 1 million years. Well, now we can ask the question. I can make it a bit bigger. We can ask. 1 second. We can ask the question: what role did climate change actually play in our human migration and also evolution? And there are three main drivers actually of these long-term climate shifts. One is the change in Earth's axis tilt. It's called obliquity. The other one is, and it has a time scale of about 40,000 years. The other one is a change in the eccentricity of our orbit around the sun. This is, has a time scale of about 100 to 400,000 years. So currently, for instance, the orbit around the sun of our Earth is very circular, but around 100,000 years ago, it was relatively, was much more shaped like an ellipse. And we have Earth's axis wobble. It's called also precession, and it has a time scale of 21,000 years. So what these drivers do, these astronomical drivers, also called Milankovitch cycles, is they change the insolation, the solar radiation that our Earth receives as a function of season and latitude. And what it does is these drivers and solar radiation, they shift climate patterns on our planet, such as vegetation, precipitation, ice sheets, and so on. And this is on the long term. So you can imagine if we have a situation where there is a lot of rainfall, there is also going to be much more food available. So you will end up in a situation where, for instance, lots of herbivores can gather, and as there is food available, also humans congregate, and they try to, as predators, they try to, of course, obtain food. So this is kind of a pull scenario, how climate essentially brings life together. But we can also think about the divergence scenario when there is essentially a drought in an environment which cannot support enough life. You can also have the situation where groups start to separate and migrate into different ways. And that can lead to genetic diversification eventually, and also speciation. Okay, so what we would like to do is we want to quantify the climate-human linkages. How do we do that? We need to first know who lived where, when, and what were the climate conditions back then. So in order to address the who, where, and when, my group collaborated with the Professor Pasquale Raya from the University of Naples, and he developed a very large compilation of fossil and archaeological data of early humans. And what you can see here is essentially a table, and it includes the human species, for instance here Homo erectus, that's this group that lived from about 2 million years to about 400,000 years ago. We have the longitude and latitude where these specimen or some of their tools were found, and we can also date how old are these specimen, and there is also dating uncertainty, of course. So we have some information on who, where, and when. What's still missing is the climatic information in order to better understand the evolutionary question. Well, in order to estimate what the climate conditions were, let's say 400,000 years ago at a particular location, we can either look for paleoclimate data, that could be sediment cores, that could be data from cave deposits and so on, but they're very sparse. What we can do instead is to use a climate model, and later on I will talk a little bit more about what actually a climate model is and what it includes, but here I would just say it's a computer code that solves the physical equations of the climate system: atmosphere, ocean, ice, vegetation. These are complicated equations, so we need a supercomputer. And we used a supercomputer, Aleph, which is actually very close is directly in the IBS headquarter center in Daejeon. And this supercomputer was able to simulate the climate system evolution over the last 3 million years. And what you're seeing here is just the time evolution of the global mean surface temperature. But of course, the model simulates climate everywhere on our planet on a certain grid. So we can look at the North Pole, we can look at the deep ocean, all of these things are included. However, here I'm just averaging the global surface temperature. And you can see the main cycles here are these Milankovitch cycles, the waxing and waning of the ice sheets. The major ice sheet starts here. This is a timescale of about 100,000 years. And currently we are here. We actually also ran the model into the future, but this is for later. And the key point here is that our climate model simulation captures the temporal range of early human evolution, including 5 different species that we will take a look at. So what do we need in order to conduct these climate simulations? I mentioned already, we need to have information on how Earth's axis rotated, how Earth's orbit changed over time. So this is something that we can obtain from astronomical theory. We also need to know the ice sheet evolution, how it changed over time. And we need to also know how the greenhouse gas concentration, CO2, etc., changed over time. And this is information that we can extract from ice cores. So this is something that we call the forcing. The forcing will be applied to a climate model. We'll talk about it later. And then, together with the who, where, and when, we can also include the what climate conditions existed at that time. And now, from this information, we can essentially build a statistical model that tells us, given the climate conditions, how likely would it have been for a particular human species, let's say Homo neanderthalensis or so, to live at a particular time and point. So we can calculate probabilities. And that's what we are seeing in the next slide. The next slide shows the average, what we call habitats, of different human species. Each of these dots represents an archaeological or anthropological specimen. So it could be a skull, it could be a teeth, it could be a tool that we can attribute to a particular human species. And in the blue shading in the background, you can see the likelihood over time for these humans to be in this particular area. And it's quite clear. Let's focus here on the Neanderthals, some of our human cousins. Mostly they like to hang around in Eurasia, mostly Europe. And in the background, you can see clearly this is a most suitable area. Now, if we go back, for instance, to this group Homo heidelbergensis, which plays actually an important role in our human evolution, we can see this group lived in Eurasia, but also in Eastern and Southern Africa. And there are certain areas that are apparently particularly suitable for their livelihood conditions. And okay, so this gives you an idea that these 5 different human species actually had different habitat preferences. They like different climatic conditions. But it's not only that that we need to look at the average conditions, but we also need to look at how these conditions changed over time. And what you're seeing here is just for a few points, you can do this pretty much for a lot of points, every 1 by 1 degree as we calculated it, the habitat suitability, so the likelihood to find a particular human species at a given point. Let's focus here on this location in Germany, Neanderthal, where actually the first Neanderthal skull was found. And we can see here over time the probability to find these groups changed. Sometimes it was very high in the warm conditions, and then during cold conditions, the habitat suitability was very low because during these time periods, there was an ice age and the Neanderthals moved further south to the Iberian Peninsula and to the Mediterranean. So from this calculation that combines archaeological data as well as climate model data, we can now build the picture of where and when these human species may have lived. And that can also give us additional clues on their adaptation and potential speciation, as I will show in a minute. Well, first of all, we can check at every location and time where we have a human fossil, for instance. All of these dots are essentially human fossils or archaeological specimen. We can look in our climate model, what was the net primary production? What is net primary production? It's essentially a measure for how much food is available due to the environmental conditions. We can calculate this in a climate model. And clearly over about 2 million years ago, we could see the evolution of the net primary production and of this very early archaic African Homo, this Homo ergaster and Homo habilis, two groups. And they were relatively confined to a region between 200 to 400 grams carbon per square meter per year. So that's a reasonable range. However, as the new human species emerged, we see that the food resources that they are using expanded tremendously. In particular, we see that now this new human species, Homo heidelbergensis, which started around 800,000 years ago, was suddenly able to adapt to much, much drier conditions with much less food. And then later on, we also see, of course, Homo sapiens becomes like a very universal figure and was able to go from very dry conditions, desert conditions, all the way to very wet rain forest conditions. So what you're seeing here is the adaptation of different human species to different types of food resources. First, these are specialists, then they start to move into other areas from Africa actually into Eurasia, where they encounter different vegetation conditions, such as forest areas and so on. And they had to adapt to them, and that is very clear by looking at the food availability at the locations where archaeologists and anthropologists found skulls and tools. And so on. And this is actually interesting because it follows also a little bit this evolution of our brain size. So the more capability we have to think and socially interact, the better it is for us to obtain food resources under extreme conditions. So we adapt to climatic stress. Another thing that you see is also, along with this adaptation and also evolution of our brain size, also our tools became more and more sophisticated over time. And about 600, 700,000 years ago, Homo heidelbergensis was able to obtain the controlled use of fire. All right, so that is just giving an idea how we adapted through migration to different climatic conditions, and we became essentially a universalist, starting from a specialist about 2 million years ago. Now, who was the ancestor of our Homo sapiens group? Homo sapiens, as I mentioned, started around 200 to 300,000 years ago, somewhere in Eastern Africa. In fact, the first skull that was found is about 230,000 years old, Homo kibish. But if we look at the genetic history of our Homo sapiens species, we can see that many of these groups that we can trace back with current genetic methods, they kind of converge in around 200 to 300,000 years ago. And what's interesting is they converge towards a group which is called L0 haplogroup for mitochondrial DNA, which nowadays is still very prevalent in Southern Africa. So it's possible that Southern Africa may have been like the cradle of mankind or humankind. And by the way, this is the little branch that started around 100 to 60,000 years ago of individuals that eventually left Africa and started to settle and populate Eurasia and other regions. Okay, so in addition to this notion that there was this convergence around 200 to 300,000 years genetically, we can also see that we have Homo sapiens skulls. We have the Homo heidelbergensis skull around 300,000 years ago, and something which is a bit more like a hybrid around 260,000 years ago that was found in Southern Africa and Florisbad. So there is this idea that maybe what we are seeing here is a speciation, a movement from essentially Homo heidelbergensis to this hybrid and eventually Homo sapiens. So this is just indicative. So in order to test this, we need to look at how the habitats change, because a hybridization or speciation event requires these groups to have shared a common habitat. And using this habitat analysis that we discussed earlier on, we can then look at where and when did these different groups share a habitat. And I will just show you the result. It turns out that, first of all, this group Heidelbergensis shared a common habitat with Homo neanderthalensis around 400,000 years ago in Eurasia. So most likely this Neanderthalensis group, Neanderthals, they emerged from this earlier group, the Eurasian Heidelbergensis. Now, for us, for our own species, Homo sapiens, it turns out that the only time where we really shared a habitat with this Heidelbergensis group was around 300 to 200,000 years ago, and that was only in Southern Africa. So here is a mathematical, quantitative evidence for this shared habitat that is a requirement for a speciation event. Let me just summarize this picture here before we move into the present and future. We are currently somewhere here. So this is our genetic ancestry that we can trace back. We talked about this merger of all current mitochondrial DNA and also nuclear and Y chromosome DNA groups currently about 300,000 years ago in Africa. Where exactly is still a matter of debate. I think there is good reason to believe it was in Southern Africa. And even this African group probably emerged from this earlier group, Homo heidelbergensis. However, this group itself split into an African and a Eurasian branch around 600,000 years ago. And all of this happened within changing climatic conditions. We had the ice ages going back and forth. We had major shifts in the precipitation on our planet driven by Earth's axis wobble and so on. So we can see you have the climatic evolution, and somehow embedded in there we have our own human evolution. Now, this Eurasian group of Heidelbergensis eventually became Homo neanderthalensis, and another group, Denisovans, which is a bit an elusive group. We know about their existence from very few skulls, but mostly from DNA. So there is clear evidence that humans actually interbred with Neanderthals. I have 2% Neanderthal DNA. Some groups nowadays, in particular in Melanesia, they have about actually 6 to 8% Denisovan DNA. So there is clear evidence that these groups were not just separated, but they were actually interbreeding events. Now, let's move to the present. The question here is, when did we actually start to change climate? Previously, we were changed by climate, but what is the evidence for us changing the climate, and when did it start? And I would like to give you a historical perspective here. Alexander von Humboldt, one of the German discoverers, explorers, adventurers, and natural climate scientists. He did extensive travels across Asia and South America. And in 1844, he wrote an interesting book, which can be regarded as the the founding of modern climatology. In this book, he says, climate can change, and it can be changed. So the German, I'll just translate it, is the human changes the climate through cutting down forests, through changing lakes and river systems, and through emitting gases in the centers of industry. So this is 1844. This is essentially before we even talk about the Industrial Revolution. He already had the sense that humans would become a main factor in driving the climate system into the future. And I just wanted to give a perspective here on the map, the background map of his travels. And these are key locations where Alexander von Humboldt traveled in his extensive discoveries. And what we are seeing here are the temperatures, essentially, since he visited these places, if temperature data are available. For instance, Berlin. Well, that's where he grew up, that's where he worked initially. And in Berlin, the temperature has gone up essentially by 2.5 degrees Celsius over the last 180 years. Well, let's take a look at, he visited, for instance, South America, and also there we see the same thing. Temperatures went up dramatically. He visited Eastern United States. Also there we can see a very clear trend towards warming. So, of course, we know nowadays that we can attribute this warming to human interferences, but already at Humboldt's time, he had a clear sense that the climate was changed by our factors. And this is just looking at the global mean surface temperature from 1850 to present day. And you can see very clearly there was a relatively stable period, a rapid increase, stable period again, which is a competition between aerosols and CO2. And then since the 1980s, of course, we have really seen this global warming trend emerge very, very clearly. Industrialization, urbanization, in particular, the input of CO2 into our atmosphere are the main drivers. But I think it's important to also look at the natural factors. Volcanoes, for instance, when a large volcano goes off, we have lots of aerosols, sulfate aerosols in the atmosphere, and they dim the sunlight, so it leads to a cooling effect. And in fact, some of these changes in the global mean surface temperature can be attributed to volcanic eruption. This is, of course, the Krakatau eruption. We have Pinatubo, El Chichon. And so these events, they can cause temporary cooling of our planet of about 0.1, 0.2 degrees, but it just lasts for a few years and then it recovers. So clearly volcanoes play a role in creating some of these dips, but they are, as in fact already hypothesized by Alexander von Humboldt, they are just having a temporary fingerprint. Well, now there is another feature. This is the El Niño Southern Oscillation phenomenon. It is a warming and cooling of the eastern equatorial Pacific, and this was supposed to be, click on it. This is showing the temperature changes in the eastern equatorial Pacific as simulated by one of our climate models. And the warming of the eastern equatorial Pacific, which we refer to as El Niño, is the largest naturally occurring climate phenomenon on our planet, and it can create global temperature changes in the range of plus minus 0.1, 0.2 degrees Celsius. So some of these global temperature wiggles that you can see here can be attributed to major El Niño events. However, the trend itself cannot be explained by this. Let's move on to the next one. Of course, due to the introduction of aerosols and CO2 into the atmosphere, we have this combination of aerosols have a cooling effect. That is one of the reasons why the temperature started to stabilize here, because there was a lot of dirty pollution in the atmosphere. CO2 has this warming effect, and since the Industrial Revolution, we have a massive increase of CO2 in the atmosphere. What does it do? CO2 is a greenhouse gas, a naturally occurring greenhouse gas, which serves like a blanket for our atmosphere. So what it prevents is the infrared radiation that wants to escape to space from our surface is partly absorbed by the CO2 in the atmosphere, and part of it gets actually backscattered to the surface, creating additional warming. This is a naturally occurring effect. However, what we do as humans is we enhance this effect by putting more CO2 in there and by making this blanket, unfortunately, even more efficient. Now, let's talk about the future. The main carbon problems that we have are due to fossil fuel burning. And there are several carbon problems that we need to address. One is, of course, global warming, as we just mentioned. Global warming is causing extreme events, heat waves. It's responsible for sea level rise, changes in human livelihoods, water resources, food security, changes in ecosystems, health, etc. We have also another effect, we will talk about this later on. It's called ocean acidification, and the CO2 that we emit into the atmosphere, about 30%, a little bit less, gets absorbed by the ocean, where it creates a chemical reaction which changes life in the ocean dramatically. And that's something we should also consider when we think about reducing CO2. There is another effect, ocean hypercapnia. If some of that CO2 is being taken up by the ocean, fish will see a higher CO2 concentration, which actually influences their metabolism and their entire behavior. And you know that in a lecture hall, if too many people, if there is no fresh air, CO2 increases in a lecture room dramatically and become a little bit tired and drowsy. So this is something similar to what fish experience when there is too much CO2 in the ocean. That is a state that we will reach in about 150 years from now, unless we cut down CO2 emissions dramatically. Air pollution, of course, is maybe the largest killer of humans related to CO2. There are estimates that millions of people actually die prematurely of air pollution in India, China, and probably also partly in Korea. So this is something we need to consider. Let's talk about these factors. And the main issue is that CO2 that we emit into the atmosphere will stay there for a very long time. It turns out that the CO2 that we emit today by, for instance, driving a car or turning on the AC will stay for about 8,000 years in the atmosphere, or after 8,000 years, 30% of it will still be left in the atmosphere. So this is called the carbon legacy problem. And it means that even though we can cut down our CO2 emissions, the CO2 that had already been emitted into the atmosphere for the last 150 years will still be up there for a long time, until gradually it's been taken up by the biosphere and the oceans. Now, let me talk about this bending the curves, because that's really an important concept here. So these are the CO2 emissions. So every year, so currently we emit about 36 gigatons CO2 equivalent per year. And this number, well, is extremely high, is the highest ever recorded. It is driving, because these are the annual increments that are added into the atmosphere, it's driving the CO2 to increase. Now, we don't know what's going to happen. Hopefully, we will not continue to emit CO2 into the future. We can say this is a scenario, but if we continue to increase our CO2 emissions by 2050, and then gradually reduce towards the end of the century, CO2 will only stabilize at a certain level when the net zero emissions turn out to be zero. So this is something to consider, that the CO2 emissions can be reduced to zero, but the CO2 that had already been emitted into the atmosphere will stay there and cause global warming for a long time. Now, people talk about net zero, so hopefully that works, but we can discuss that maybe later on in the Q&A, what the current political situation is. From the current emissions, if we want to go down to net zero by 2050, as pledged by many countries worldwide, including Japan and also Korea, in that case, by 2050, the CO2 concentrations will start to stabilize and then gradually over 8,000 years decrease. So, of course, becoming carbon neutral earlier means we are also having less of a warming into the future. But there is another important point. So we talked about the emissions. Hopefully we can stabilize them early, because once the emissions decrease to zero, CO2 stabilizes, and also, interestingly, temperature kind of stabilizes. But it turns out that even if the CO2 is relatively stable, temperature will still start to increase a little bit. It's because of the thermal inertia of the oceans. Now, there is a different story here. And the different story is that if our planet exceeds 1.8 degrees Celsius global warming, keep in mind we have already reached 1.2 degrees warming. If we warm up our planet 0.6 degrees Celsius more, then ice sheets, such as the Western Arctic ice sheet, will continue to melt. We reach the point of no return for these ice sheets. So this is something to keep in mind, and that will continue to sea level rise. So only if we stabilize our warming to below 1.8 degrees Celsius will we be able to stabilize ice sheet demise and sea level rise. However, if we go beyond, these ice sheets will continue to contribute to sea level rise in the future, even though we may become carbon neutral at that point. So that's a big danger. So how can science help? There are several aspects here. Knowledge, of course, prediction, and hopefully also solutions. And I would like to give you some perspective here on how we actually learn, how we obtain information about the future of our climate system. I already mentioned earlier on a climate model, which we used in the past, but we can also run a climate model into the future. So first of all, what is the climate model? Well, the climate model is just a gigantic computer code, mostly still written in Fortran. About 1 million lines is a typical climate model. What does it include? It solves the equations for fluid dynamical equations for the atmosphere and the ocean. It includes thermodynamics. It includes quantum mechanics, because the greenhouse effect is a quantum mechanical effect due to the absorption of CO2 and other greenhouse gases. And it includes electromagnetism, which is essentially radiation on our planet. We also need to capture how, for example, trees grow and how vegetation changes, how marine productivity in the ocean changes, chlorophyll, and so on. And these are equations that we call parameterizations, so they include our best empirical knowledge. And we need the forcing, so we can play with different scenarios. What if we become carbon neutral by 2050? What will the climate system be looking like? What if we don't do it? What if we continue to blast CO2 into the atmosphere? So this is kind of our turning knob, the scenario knob, where we can say, well, given a certain socioeconomic scenario, what will the climate system look like? And these are very complicated equations, so programming them requires many years and many scientists of work that generate these computer codes, and they can only be cracked on the largest computers on our planet. And one of them, as I mentioned, is the Aleph supercomputer, very close by For those of you who attend in person, it's in the next building, in the IBS headquarter building. There is a supercomputing room where you can see Aleph, and it's one of Korea's fastest academic supercomputers, mostly dedicated for high-performance supercomputing. And it can do about 1.5 quadrillion calculations per second. So that is a way of cracking these equations. Okay, I hope I can run this. So the climate model is solving these equations, and it's outputting large amounts of data of ocean currents, ocean temperatures, salinity, of atmospheric winds, atmospheric clouds. Everything is included essentially, and then you can visualize or you can analyze these data statistically. And what you're seeing here is a visualization of the ocean currents in this area, Korea and here are the Philippines. And every once in a while you have eddies, you can see these tropical cyclones running through and changing the ocean currents. So this is the level of detail that we can resolve with the climate model. Now, giving it a more static view here, as we run the climate model into the future, we can then see how, for different CO2 configurations, how the planet will warm up, or how winds will change, how rainfall will change. So this is for a business as usual scenario. We keep emitting CO2, we don't do anything. I hope we can avoid this. In this particular case, in the next 80 years or 78 years, our climate system will warm up tremendously. The Arctic Ocean will warm up by another 10 degrees, 4 degrees Celsius warming in Korea. If we continue this whole scenario into the future even further to 2150, so 130 years from now, the planet will be looking very differently. We will have 15 degrees Celsius warming in the Arctic, 8-degree warming, and so on. So this is pretty dramatic, but nevertheless, it makes the point that CO2 is really the driver for massive changes in the climate system. Now, here is the prediction for, or projection as we call it, not a real prediction, but projection given a certain CO2 scenario for rainfall over the Mediterranean region. If we don't cut down CO2, in the next 78 years, the Mediterranean will dry out by about 25%. This is massive. This would be a mega drought of unseen proportions, driven by human activities. And this drying is related to atmospheric circulation shifts that are triggered by global warming. A 40% drop in long-term drop in rainfall in the Mediterranean region would result in essentially this entire area suffering enormously from water shortage, and agriculture will probably collapse at that point. Okay, so another question is, we can look at not only at the mean changes, the warming and the mean precipitation changes, but we can also look at extreme events, because these climate models, they simulate extreme events such as tropical cyclones. So this is coming from our computer model simulation. Here's Japan, Korea, and you can see some of these flying donuts. These are tropical cyclones or hurricanes called in other areas. And the climate model simulates them just as a result of the fluid dynamical equations and the thermodynamic equation. And now we can give the system higher CO2 concentrations and see how do these tropical cyclones actually change. Do they change their frequency, their intensity, and so on? And what turns out is that, so if we look at the average tracks of these tropical cyclones, these are the areas where they are formed and where they move, in the future, there will be a major reduction actually of tropical cyclones. The number of tropical cyclones will decrease, except south of Japan. However, according to our climate model simulations, what we see is that the total number decreases, but the number of very strong ones actually increases. It doubles, more than doubles actually. So if a tropical cyclone forms, the likelihood that it will become a very strong one increases dramatically. Even though the total number of tropical cyclones decreases, because a warmer atmosphere can hold more moisture, we will also have more precipitation associated with tropical cyclones landfalling. So there are two things to consider here. One is less number, but increased strength. And if there is a tropical cyclone in the future, it will dump more rainfall onto our land, which is, of course, major concern for flooding. Then let me just say a few words here about the implications of global warming. We always think about heat waves. We think about our own well-being and so on. But we depend very much, of course, on food. And we can ask the question, will global warming actually influence global food security? And the consensus in the community is yes. And here is the reason why. If we look at the productivity of a crop, let's say wheat or rice, it increases. If it's too cold, there is very little crop yield. But the crop yield has a certain temperature optimum at around, I don't know, 25 degrees Celsius. That's where they like it. But if we go beyond, there is a rapid decrease in the crop yield. And it turns out that most of the current crops that we have right now, they are already growing at this optimum temperature. So any move in the temperature due to global warming will mean that we are moving more into that area where temperature starts to, where the crop yield starts to drop dramatically. And this means that with every degree global warming, for some of the major crops such as rice, soy, and wheat, there will be about a 10% decrease in global production, global productivity. So until 2100, for instance, there is a projected reduction of crops in India, South Africa, and the Middle East by 30 to 40%. So this is massive at a time in particular when population is still expected to grow. So this is something we need to consider. Food security is at stake here. Well, I would like to say a few words about another carbon problem, which is ocean acidification. So what happens is we are burning CO2. Some of the CO2 eventually ends up in the ocean, about 24% currently. And as it dissolves in water, it forms carbonic acid. This carbonic acid becomes a bicarbonate ion and a proton. There is a chemical balance equation here. The bicarbonate ion can further split into carbonate ion and another proton, and this is why we call it ocean acidification. We're increasing the number of protons, free protons here in the ocean. This reaction first seems to be maybe not very relevant, but combined with another reaction, it is actually quite clear that it has an impact on life, marine life. Well, oysters, corals, pteropods, a lot of calcifying organisms in the ocean use this equation. Calcium ions in the ocean can bind with the carbonate ions to form calcium carbonate, and this is usually this nice structure that we have in many parts of the ocean. Now, as we increase the CO2, CO2 gets dissolved into the atmosphere. This carbonate ion moves over in this reaction to form two bicarbonates. So this upper reaction essentially won't work anymore. So this CO2 dissolved in water steals the carbonate to create two pretty useless bicarbonate ions, and hence reducing the efficiency of the upper reaction. So this is essentially the nexus between humans, our CO2 emissions, water chemistry, and biology in the ocean. So there are particular organisms that are very vulnerable. So high magnesium calcite in the ocean is very vulnerable to this effect. Lots of aragonite shells and structures such as corals, shells, conches, etc., they would still be very much affected by this, and it all is already happening. Ocean acidification is happening. We can see it already. There are other marine organisms that may not be as much affected. These are the low magnesium calcite ones that are much less dissolvable. And of course, diatoms, which don't even have calcium carbonate. So this is something to consider. There will be losers and there will be winners in this equation. But what's clear is that there will be major shifts in the ecosystems of the ocean unless we cut down CO2 emissions. And this is the projection. 1850, this line illustrates where green, where calcification happens, separates from orange or red, where calcification is reduced. So in 1850, we have this natural area where we have relatively low carbonate ions, means little calcification. Then as we go into the future, this line moves to south of Korea and Japan, which means that if we don't cut down CO2 emissions, these areas will be heavily affected by ocean acidification, reducing the calcification of many of the marine organisms substantially. So, question I hear a lot is it already too late? Can we do anything about it? Well, the point is, yeah, we can do something about it. So these are essentially the current, this is this pH in the ocean acidification, this is the temperature. And yes, we have changed our planet already. Let me take this away. Depending on our current choices, we can determine whether the future will look like this, and with still healthy animals in the ocean, with still climate system that we can cope with and adapt with, or we can just say, well, we don't do anything, it's too late anyways, or we have some economic interests and so on. We don't want to change our gear towards carbon neutrality. In that case, we end up with a different planet. So the point here is that currently we can still determine global warming is still going to happen, but we can determine by how much. So it gives us responsibility, our generations, responsibility to do something for not for the current generation, but also for many future generations. And I mentioned to you, CO2 stays in the atmosphere for a very long time. Okay, so there is the Paris Agreement. The Paris Agreement, you may have all heard of it, is kind of a landmark political agreement where many countries pledge to reduce CO2 emissions, to reduce global warming to below 2 degrees Celsius above pre-industrial levels. Remember, 1.2 is already reached, while at the same time pursuing efforts to limit the increase to 1.5 degrees Celsius. And keep in mind, 1.8 is the point where the ice sheets will irreversibly start to melt. So Korea is, of course, one of the main emitting CO2 emitting countries, and we will look at this a little bit more in detail. But many countries have pledged in the Paris Agreement to do something about it. Now, we can look at what needs to be done and what has been done. So there is a very nice website, and I invite you all to go to this website. It's like a carbon economic climate emulator or simulator, if you like. What we will find on this website are essentially temperature curves. Here, you can modify the greenhouse gas emissions, and you have all these sliders that you can move back and forth. You can, for instance, look at the climate system if you don't do anything. If you don't do anything, the climate system will just warm up by 3.6 degrees Celsius. So you can see the total greenhouse gas emissions will continue to increase. And we will end up on a planet way beyond what the Paris Agreement has promised to do. Now, if we say, well, we increase the carbon price, which makes, of course, using carbon less attractive, and if we also subsidize renewables, well, in that case, the CO2 emissions would go down, for sure. but we will also have a drop in temperature. But it's only going to be 1 degree less than the 3.6. So we are still not within that range of 2%. So just carbon tax and renewables is not enough. So in order to get closer to the 2.1, we need to also, for instance, reduce other greenhouse gas emissions, such as methane, coming from industrial processes and meat production. We need to reduce deforestation in the Amazon dramatically, and then you can see the drop in emissions, net emissions, is even less, and we can get very close to this 2 degrees. But this is already a major effort for economy and also for the industry. In order to get below 2 degrees and get closer to the 1.5 Celsius pledge, we need a portfolio of different activities. It means it's not just one size that fits all. Our planet needs to really work on a combined effort: renewables, increased carbon price, increased energy efficiency, electrification, and deforestation, and reduce other greenhouse gas emissions. Only under this scenario will we be able to reduce the CO2 and the temperature enough to follow the pledges of the Paris Accord. Well, this is all theory. What about reality? It turns out that in spite of the pledges of major countries, 34 countries are still considering new coal plants, that is in 2022. China has pledged to stop all overseas emission coal plants. That's already a good step forward. It's not sufficient. But at the same time, India has agreed to reopen 100 new coal plants. So that doesn't look like we are moving into the right direction. Methane levels have been had the largest annual increase ever in 2021 and 2022. The deforestation in the Amazon is up 70% compared to last year. So we have the political promises, but reality in 2022 does not look like we are going to get there anytime soon. So it's about bending the emission curve. What do we need to do? And that requires a combination. We can't, as I mentioned, we can't just focus on one horse here. We need a combination of advanced technologies to save energy, to generate cheap renewable technologies. We need strict regulations without carbon taxes. There is no reason for the industry to switch to other alternatives, and also for any consumer. If carbon still is cheap, oil and gas, why should we change our behavior? So we need to put on carbon taxes, use the carbon taxes in order to subsidize other types of technologies. So this is incentives. So you can combine carbon taxes regulations with carbon dividends. So a government can collect the carbon taxes and use them to spend them wisely in order to create a green economy. Governance, of course, we need strong national policies, international treaties that are not just words, but that are also actions. We need societal transformations, our own behavior, local products. We need to educate not only the young generation, but I think we need to educate the old generation in particular, that it's important to save energy and do something for it. And there are also possibilities to use existing ecosystems, reforestation, blue carbon sinks in the ocean to take up some of the CO2. So we need this portfolio of activities in order to essentially save our planet from a climate crisis of unseen proportions. Well, carbon neutrality is not a stroll in the park. In order to get there, we need sacrifices. It's not like we can just keep our lifestyle the way it is. I think that's unrealistic. We need to make sacrifices. We require teamwork, dedication, and most importantly, action. So I've been to so many meetings in the last years where it's all about discussing, but I have seen very little action, and I'm starting to get really worried about it and tired of the lack of action. Well, here are just a few ideas of what you can do personally, but I'm sure you already do most of these things yourself. And this is definitely something that should be implemented in, for instance, policies. Buildings need to be better insulated. This is something that you can put into a future building policy. Houses in many regions in the world have very poor insulation, so we are wasting energy in summertime by cooling them inefficiently and in wintertime by warming them inefficiently. Shorter showers, recycling paper. I also wrote down no Bitcoin here. Why? Because the Bitcoin mining worldwide generates as much CO2 as the entire country of Argentina. So no Bitcoin means essentially you can save a lot of CO2 here. And there are lots of very simple things. This is not going to bring us into carbon neutrality, but it will bring us into the right direction, something that every individual can do. However, the big companies and governments need to also chip in their contributions. So here are just a few issues. We can put a price on carbon. We need to put a price on carbon. That carbon tax can be handed back to the consumer later on as a tax dividend system, so it becomes economically neutral. We need to divest from fossil fuels, for instance, major companies as well as retirement funds and so on. They start to divest from fossil fuels. Mentioned Bitcoin mining. We need tax incentives for photovoltaics in many countries. Rather than supporting other types of energy resources, we need to support the renewables, improve efficiency, deregulate wind farm implementations. Incredible how difficult it is for a company to build a wind farm, even though the environmental conditions may be correct. It's much easier to build a coal-fired plant than build a wind farm. The implementation is very complicated. We need to invest in green hydrogen technology and invest in science-based adaptation strategies. I didn't have time to talk about it, but this is really important. Climate change is already happening and will also happen in future. We can hopefully cut down the level at which this is happening, but we still need to adapt to the changes that will occur. We need to decentralize electricity and utilities management. This is the only way to really come up with an ecosystem of green energy solutions. And for Korea, for instance, this is a very specific case. There are very high road fuel subsidies that need to be removed. There are lots of these things, and every country has perhaps a different bucket list of things that they should be doing. But the point here is that we can reach carbon neutrality. It's a matter of not technology, it's a matter of will and action and political commitment. So with that, I'll thank you for your attention, and I will stop my screen sharing, and I'm happy to take any questions. Thank you.
Yes, thank you very much for your presentation. And now we're going to move on to the Q&A session where the participants get to ask their questions in real time to the director on the issues. Today, the director has mentioned about the humans and climate. So if you have any questions, the ones that are joining us online, please press the hands-on button. And we also have offline participants already raising their hands. I saw the person at the back raising their hands first. So yes, thank you very much. Please say your name, your country, and then go on with your questions. Thank you.
Hello, my name is Meir Ignatiev. I'm from Russia. Thank you very much once more, dear Professor, for this honestly outstanding lecture. I think it's of vital importance to emphasize on this subject a little more and to disseminate this knowledge, especially amidst younger generations. Thank you very much. My question concerns the poor countries. Due to political crises and instability that put many countries and governments into a precarious balance, and these governments, they have less cash to pay for adoption and more need of it, not least because they tend to be situated near equator, in zones where temperatures can push, where heat waves can push temperatures into unsurvivable conditions and levels. They also tend to have higher population growth, meaning that more and more people will be affected in the end. So I would like to hear from you your personal ideas and suggestions on this matter. Thank you.
Yeah, thank you very much. This is a very important point. It's all about climate justice. So the current CO2 emissions, they can be attributed essentially to rich countries. The current CO2 concentrations in the atmosphere, most of it actually came from the United States. If we look at the time integral over the last 150 years, but yet the planet is suffering, and in particular regions in the tropics will be suffering most. And these are regions with much less contribution to the problem and with much less economic capabilities to handle the problem. So this is all true what you said. There is supposed to be a mechanism. This is called the Green Climate Fund. Actually, the center, the headquarter is based in Seoul, it's in Incheon, so South Korea. And the Green Climate Fund is supposed to receive from other UN countries money that will then be used for adaptation projects or developing projects in other countries. So the idea is also that now a lot of other countries, including, for instance, India, is really picking up with industrialization a lot. So for them, switching to using old coal and oil carbon-based technologies would be bad for the future climate system. So the idea of this Green Climate Fund is to use the funds obtained from the rich countries and disseminate them to the poorer countries in order for them to not switch, not use carbon-based technologies, but for them to use photovoltaics and wind farms, etc. There are also other possibilities to use this fund. The idea is to create a little bit of a climate justice, but it's still under some kind of, I would say, post-colonial perspective and framework, which is a bit worrisome. So it is a big problem. I don't see a simple solution. Oh, by the way, there is another institution that is supposed to obtain funds from other UN organizations and distribute them to other countries. And this fund is supposed to receive 100 billion US dollars that will then be disseminated. Currently, this fund is, I think, close to 80 billion US dollars, so hasn't even reached the level it is supposed to reach. How efficient these projects are on the ground is another question, but the climate justice is maybe one of the worst parts of the climate problem. And another thing I wanted to mention is migration. So let's say the best example are Pacific Islanders in regions that experience massive sea level rise and that use essentially their land, that lose their livelihood, that lose their home, because sea level rise will inundate or is already inundating their current islands and homes. So where do these people go? And there is the discussion that there should be a climate refugee status. UN level discussions, but everybody is afraid of including climate disaster as a reason to seek for asylum in another country. Currently, there is political asylum seekers, but they don't want to open that door to climate asylum seekers. So many countries have large objections, and I think it's a big problem. because this is the only way for some countries essentially to survive, to be able to resell to other regions if their home, an island in the in the Western Pacific, is gone in 30 or 40 years from now. So I don't have a solution. There are supposed to be mechanisms, but I'm not quite sure if they're very efficient right now.
Yes, thank you very much for the answer. You have just mentioned about the institutions that can back the adoption as well as the development projects of the poor countries, and alongside with other topics such as the climate justice and migration. And now we're going to accept another question. And now why don't we accept a question from the online participants from Zoom? I guess there will be participants who are raising their hands as well. So if you raise your hand using the icon raise hand button, we're going to give the person the chance to ask questions. So do we have participants from Zoom who can, so yes, if you can show us the Zoom screen so that we'll be able to see if there's any participants with questions. Yes, please introduce yourself and go ahead with your question.
Can you hear me?
Yes, I can hear you.
Good morning, everyone. Really pleased to be here, especially here with Dr. Timmerman. I'm Leighton Mershkotis from the Philippines, specifically from University of the Philippines. My question is, are we evolving to survive the extreme conditions on climate change and pollution? Because I just saw an article talking about adaptation of marine creatures consuming microplastic, as well as I saw a biotechnology documentary on Cleo Abraham about genetically modifying trees to efficiently photosynthesize. So I'm wondering, are there records in history when these species adapt to conditions to evolve their genetics to withstand extreme conditions? Thank you.
So adaptation usually takes a long time. And so adaptation in our behavior can be fast, right? But adaptation on a DNA level is a much longer process. Usually, there are exceptions for that. So your question is whether we can evolve in some way and adapt to it. I think we will, as a species, adapt to it. The question is who will adapt to it? If there is a way in future, and I'm just speculating, if there is a way in future, I'm pretty sure rich countries eventually will manage to find ways of coping with the problem. Let me just give you an example. Sea level rise in the Netherlands is not a big problem. Netherlands is even partly below sea level, some areas, because for the last 300 years they have built dike systems, they have built sophisticated pumping systems. It's a rich country that will withstand future sea level rise because they have the technology which they can implement. Bangladesh is extremely low, lying very close to sea level, and already a sea level rise of about 50 meters will inundate huge areas of Bangladesh. Bangladesh has a very high population density. Many people have to move. There are already climate refugees in Bangladesh that move further inland to the higher elevations. So this country does not have the capability, economic capability, to build a dike around the Indian Ocean that prevents water from coming in or pumping water out. So again, there will be winners and losers to this adaptation to climate change. But I am afraid that this will further intensify the economic gap between rich and poor countries. So the climate change problem is one where it's a matter of survival in the true sense of the word, not as a species, but as a country, as a population, and as maybe ethnic identity. If, for example, people in the South Pacific from islands such as Tuvalu have to move somewhere else because their islands won't exist in future anymore, right? The islands where maybe their ancestors for a few hundred generations have been buried. These islands don't, does the country even exist in future, right? So there are fundamental questions that have not been addressed. Biologically, I think we will survive. How exactly, I'm not sure, but also keep in mind, global warming is not only affecting us, it is affecting also livestock. It is affecting everything that we eat. So global food production is in danger. And this is something which we need to address. I don't know how to overcome this climate injustice thing, but I worry that global warming will cause unproportionately large damage to people, countries, ecosystems that have not contributed much to the problem themselves.
Yeah. Yes, thank you very much. It is a question of who is going to adapt to this changing circumstances. And even though there will be a lot of economic gaps and also fundamental questions that we will have to address. The director have mentioned the problems such as the food production and the sea level rise as well. And now we're going to accept questions once more from the floor. The offline participants. Yeah, I think he raised his hands. Yes.
Hello, my name is In-hyuk Kang from South Korea. And first of all, I'd like to thank you for the great lecture that you gave, especially the part where you linked the archaeology and climate change was very interesting. And I just had a question on the average global temperature of the Earth's surface, because I heard you say that a lot when you were trying to explain the rising global temperature. But as you know, the summers these days, the summers are getting hotter and the winters are getting colder. And for example, if the average temperature of the summer raised by 10 degrees and the average temperature of the winter dropped by 10 degrees, then the temperature of the global, the Earth's surface would be the same, right? Which I was curious about how these kind of climate changes can be shown in the graphs, and yeah, that's what I was curious about. Thank you.
So first of all, let me correct you. The winters are also getting warmer. So I don't know where your statement comes from that the winters are getting colder. In fact, the winters are warming faster than the summers. And in particular in high latitudes, it has something to do with a decrease in snow cover and so on. So both increase, summer and winter on a global scale. You can have regionally and temporarily, you can have situations where you have a cold winter for sure. But the long-term trend is warming in all seasons. So that's why also the annual mean itself increases. So there is no stronger winters. It's not correct.
Thank you.
Yes, thank you very much. The director have mentioned why current climate change is such a critical issue, a matter of our survival. And now we're going to move on to the next question. Once again, we're going to accept it from the floor. Yes, from the very front row. Would you please stand so that we can deliver the mic to you? Thank you very much.
Okay, hello. My name is Kwon Yoon from South Korea. First of all, Professor Timmerman, I really thank you for your fantastic presentation for us. Okay, my question is about the future where the humanity has failed to control the carbon emissions. You mentioned several times that the deadline to the temperature rise is to 1.8 degrees Celsius. If the humanity fails to control the greenhouse effect and global warming, so the average temperature goes up to, like, for example, 3 degrees Celsius, the the phenomenons like sea level rising will continuously happen. Do you think the humanity will still be able to survive those conditions? Because the humans have survived some global disasters like the ice ages. So even though we failed to control this global warming, would the human being still be able to survive out the disasters? I would really like to hear the answer from you. Thank you.
So, as I mentioned before, I think the human species will survive. But food production is my biggest concern, that at a time when population still increases, we are starting to get into a range where global food production will start to decrease because the major crops that we grow will show this drop in the yield. And there are many companies that try to genetically modify crops to withstand climatic stress. So they were successful in modifying crops to become more drought resistant, so use less water. However, because the temperature sensitivity of a plant is distributed on so many different loci of the DNA, so far no company has managed to make temperature resistant crops. So you can imagine that if we run into a situation of global food insecurity, that we will have massive migration, probably political instability, sea level rise is contributing to this migration issue, and everybody, of course, asking the main countries, the main CO2 contributing countries, for compensation. This will be a very different world. We will survive it as a species, I think, I hope. But the level at which, let's say, future generations, the welfare of future generations will be severely impacted, and again with this rich-poor gradient amplifying over time. So survival as a species, I think, is possible, but survival of individuals who will be affected by the impending food insecurity, maybe not.
Yes, thank you very much for the answers. Yes, we will be able to be survived, but there will be major issues that will be caused alongside of this effects, such as the global food insecurity, causing other major issues as well. And now we're going to move on once again to the online platform Zoom in order to find out if there are any participants with questions. Please use the raise hand icon in order to present your questions. And as you do, we're going to select one participant from online who have picked the raise hand button and show your face to the screen. And as your face is shown to the screen, please introduce yourself and go on with your question. So let's find out who we have in Zoom. Yes, would you kindly show us the Zoom screen? Yes, now we have a participants. So please unmute yourself, introduce yourself, and go ahead with your questions. Sorry, we can't currently hear you.
Hello, can you hear me now?
Yes.
Okay, yeah, my headphones are old, I'm sorry. So I am my name is Christian Champrapab. I'm a representative of Thailand, and I have a question to ask you. So the question regards future alternatives to fossil fuels. So currently, burning fossil fuels is one of the main ways we produce energy, and there's only a few renewable sources. But what would you say is the most promising renewable source that we should do more research into in the future that could yield the best results?
It depends on the country. Let's just say for Korea, I suppose maybe also for Thailand, photovoltaic is of course a very good resource because there is a lot of sunshine. In other countries, maybe winds are more suitable. And of course, these are fluctuating resources. So we have sunshine only during daytime. So the amount of energy needs to be stored in order to be available also during nighttime for the industry and so on. So we need to have a better buffering capacity for the renewable resources. Batteries, green hydrogen batteries is one possibility. Other countries have large topographic gradients, so they can pump up water during daytime with the excess energy that's coming in from the winds and photovoltaics, and then during nighttime they let it run down the gradient again to generate water, hydro power. So I think these renewables, green, coupled with the right storage technology is going to be the way forward. And I would particularly focus on green hydrogen and photovoltaics and winds. We don't have to reinvent the wheel. I mean, just look at how cheap photovoltaics has become over the last 20 years. It's just amazing. And then if you, but then there are not many subsidies on this technology. However, there are large subsidies for other future energy resources. We subsidize fossil fuels a lot because we don't pay for the damage costs. We subsidize in many countries nuclear power a lot because a nuclear power station usually is not insurable for major accidents. A nuclear meltdown, no insurance company will say, yeah, we're going to insure you for a nuclear meltdown, which means the general public is indirectly subsidizing nuclear energy. And so once you strip off all the subsidies and you look at the level costs, then already photovoltaics per kilowatt hour is probably the lowest and the cheapest energy resource available. That depends a little bit on the country's condition, whether it's possible, but I still think we don't have to reinvent the wheel. We just need to reinvest the indirect subsidies into the renewables to make them even cheaper. And it doesn't make any sense to build new coal plants if the subsidies were taken away.
Yes, thank you very much. Regarding the alternative energy, the director have mentioned that potential each country holds would be different, but the important keyword would be to reinvest, not reinvent. And now the time is up. The given time is up, but would it be okay if we allow one more participant from the floor to ask a question?
Oh, sure.
Thank you. Then, I saw both of them raising their hands first, but I'm going to ask the one in the middle to ask the question.
Hi, Dr. Axel. Myself, Vasudev. I'm from India. So I had a question more on the scientific side of your research. So you said that during your simulations, you verified a hypothesis. If you would be so kind to introduce that hypothesis and the confidence level with which it was either accepted or rejected, and the sigma value as accompanying that confidence interval, then it will be great. Thank you.
I'm not quite sure what you're referring to. Are you talking about the human habitat simulations? Are you talking about future climate change? Because I introduced a lot of
Okay. So future climate change simulations.
Okay. So we are not the only one doing these future climate simulations. There are about 60 or 80 groups worldwide. Each of them has their climate model. And they are run under under the same forcing scenarios. And I mentioned the scenario is a socio-economic choice, right? We can't predict the future of political decisions. So we just say, given a certain scenario, like this CO2, what would a climate model generate? And then using, let's say, 60 different climate models, each of them with slightly different parameters, representations of certain processes. We can then look at the uncertainty range of these projections. And for instance, the CO2 doubling following a particular scenario by 2100 will generate a global mean temperature change of about 4 degrees Celsius plus minus 1.5 degrees Celsius, 1 sigma level. And if you're interested in more details, you can do this not only for temperature, but you can do this for precipitation, for everything at every grid point on our planet, and you will receive an idea of the amount of human-induced trend versus the statistical uncertainty. And this is all summarized in the IPCC report, the Intergovernmental Panel on Climate Change, the recent assessment report, sixth assessment report. You can look at the summary for policymakers, or chapter 4. There are figures in there where you can look at the maps of our planet, many different climate variables, and you can figure out exactly at which location are you, how strong is the trend as compared to the natural variability, the sigma level. But for global mean temperature, you can say plus minus 1.5 is a 1 sigma level, and then 4 degrees is the mean state change.
These simulations are published, right? Like the data?
Oh, yeah. You can analyze them. The data are all available on the Earth system grid and on the IPCC data server.
Okay. Thank you very much.
Thank you.
Yes, thank you very much. We're going to end the lecture 1 with Director Axel Timmermann here. So why don't we give him another big round of applause?
Thank you all for joining.
Yes, thank you very much for joining us today, Dr. Timmermann. And as we let him go, I'm going to make some announcements. As this is the end of the morning session, we will be back at 2 p.m. Korean Standard Time in order for us to begin the lecture number 2. So make sure that you be here with us beforehand. Maybe 1:50 would be perfect. So as we are to begin at 2 o'clock, please make sure that you come back to this room before time. So online participants, make sure that you log into Zoom at 1:50. And now for the offline participants, we will be having our lunch at the 3rd floor, and our leaders of each team will be happy to guide you there. So we'll see you all at the afternoon. Thank you very much. Well, before we start, I would like to remind all the participants for all of our safety, please keep wearing your masks at all time, covering your nose and your mouth. Make sure that your mask is covering your nose and your mouth. Thank you very much. Please make sure you're wearing your masks for all of our safety. And with that, we're now going to begin the second half of day 1 here at Asia Science Camp 2022. So, as the broadcast is being lived, we're going to begin the program. Welcome back to Asia Science Camp 2022, Day 1 with me, Shinjie, as your MC. Now we are going to turn to lecture number 2 under the title of Exotic Nuclei and the Universe. We have Kevin In-sik Han, the director of IBS Center for Exotic Nuclear Studies, to share more about the details on our topic. So when I call upon his name, please give him a big round of applause as he comes up to the stage. Please welcome Director Kevin In-sik Han.
Thank you very much. I hope you had a nice lunch and hope the lunch wouldn't make you sleepy, especially when I talk about physics. I know how a lot of high school students do not like math and physics these days, but I'd like to give my talk such that I hope you get some interest in physics in general, and also I'd like to share the exciting new discoveries and the future prospect for this exotic nuclei and the understanding of the universe. So so I'm Kevin In-sik Han, as I was introduced. I'm the director of Center for Exotic Nuclear Studies at IBS. So even the title might be a little bit confusing, but however, by the end of my talk, I hope you will understand why exotic nuclei, which is the microscopic matter, somewhat very strongly connected to the universe. So scientists need to ask a lot of important questions, and really good scientists try to find the right answers. So asking the right questions are very important. So I don't know how it's going to work out, but all the students at this hall, you can actually interrupt me by asking any questions, and I'll manage the time. So don't worry about the time. But anyone who's in the online, I don't know how it's going to work out, because I may not see anyone raising hands or sending text messages. So it may not work really well, but I want you to know you are welcome to ask any questions during my presentation. So questions of some of the physicists and astronomers and other people, even general public, may ask important questions like, how does the sun shine so many years? For the longest time, up until 1950s and 60s, no one knew the right answer. But we all know the importance of the sun, because it actually, that's how the nature, animals and plants live. And we still don't know where the heavy elements that you see in our body and even in our, this mic and even desk are coming from or came from. So, and we also don't know the evolution of stars. Not 100%, we have some ideas. So all these questions, you need a lot of important inputs from physics side, especially nuclear physicist. So I'm going to explain nuclear astrophysics in the later slides, but this is where I'm coming from. So does anyone know who this person might be? It's a well-known picture in the web. Because of lack of time, I'm just going to give you the answer. It's Einstein. Yeah, very pretty when he was young. Now, this is a real question. So, who am I? And so, I was born in Nelson, New Zealand, 1871. It's very difficult. Okay, you even have... Okay, maybe I'll give you another hint. So you said your answer is Rutherford. Now, I was knighted in 1914 and died in 1937. It's very difficult to tell. And I won Nobel Prize in Chemistry, 1908. What is your name? Okay, okay. One answer, Rutherford, Marie Curie. Okay, so one of you are right. So now I think everyone knows. He discovered alpha and beta particle in 1898. So the right answer is Rutherford. So let's give him a big round of applause. Very impressive, because a lot of people these days do not even know when your parents was born. So. Not you, okay. Great answer. So he devised the method of counting alpha particles with his, one of his students, Geiger counter. So he is the one who discovered the nucleus. That's where nuclear physics was considered to be studied. So Sir Ernest Rutherford, he was credited to discover atomic nucleus in 1910. That's almost 110 years ago. He actually won a Nobel Prize in chemistry because back then, smaller ones considered to be chemistry and big ones, mechanics and all those things, universe considered to be astronomy and physics. So didn't really realize the quantum mechanics and the importance of nuclear physics or physics in general play to understand other fields of science like chemistry and biology these days. So what are the matters made of? Two serious questions that physicists always ask is, what are the fundamental particles? And what are the fundamental forces? So most of you aware of this the periodic table. We all know hydrogen and all those things, uranium and so on. But are the atoms fundamental particles such that you cannot, break any smaller pieces? The answer is no. Atoms are not fundamental particles. So physicists and chemists and others, other scientists, trying to understand what are the fundamental particles and what are the fundamental forces. I'm not going to talk about fundamental particles today that much, but I will talk about fundamental particles. So, virus, coronavirus, it is actually made of molecules. Molecules are the combination of many different atoms, and atoms consist of nucleus in the middle and the electron circling around. So fundamental building blocks for nuclear matters are nucleus. And we knew that through the discovery of Rutherford, that even though protons and protons, they are supposed to repel each other because of Coulomb forces, they somehow hold together in a very short distance, which is, the distance is the femtometer, 10 to the negative 15th meter. So actually, yeah, this is a nucleus. So until 1960s or 70s, that was sort of like the fundamental particles, but not anymore. The fundamental particles these days are, what are the answers? What are the matters made of? Again? Okay, great. Okay, quarks and leptons. That's the current correct answers. And you may ask, how do you know if the quarks are also made of some smaller particles? Some physicists think they are not fundamental particles. Some people, physicists, even my colleagues, think everything is made of strings, superstrings, but they are not proven yet. So at this time, at this moment, the correct answer of the fundamental particles of matters are quarks and leptons. Leptons are smaller particles, fundamental particles like electron, muon, and tauns. Okay, very good. Now, oops. So nuclear, atomic nucleus. These days, physicists do not even call atomic nucleus. We just call it nucleus because everybody knows when you talk about nucleus, it's not atomic nucleus. It's not nucleus in the cell. We're talking about the matter. So nucleus consists of this neutron and protons, and protons and neutrons are smaller particles. They both were made of 3 quarks. So that's our current understanding of nucleus. Now, isotopes, what are the isotopes? If you have 1 proton, we call it hydrogen. If you combine proton with a neutron, it's a deuteron. If you add electron, then it becomes a deuterium. Okay? But in symbols, we put H2 right here in a superscript. And if you have 1 proton with 2 neutron, we call it triton. Or if you have an electron, then we call it tritium. However, these considered to be isotopes of proton. So isotope means nucleus with the same proton number. So what about helium case? Okay, you have helium. Helium has 2 protons. If you have 1 neutron, then helium-3. If you have 2 neutrons combined, it's called helium-4. We actually have helium-6, even helium-8. Okay, so isotopes means there's a P in here, so you can remember as, okay, we are having the same, iso means the same, topes, protons numbers are same, so we call it isotopes if you have the same proton numbers. However, some isotopes are stable, some isotopes are unstable. Unstable isotopes, we call it radioactive isotopes. That's the correct word, radioactive isotopes. For example, carbon-12, carbon-13 are stable isotopes. Carbon-14, carbon-15, carbon-22, carbon-26, they are radioactive isotopes. So whenever I said I study fundamental of properties of radioactive isotopes, they said, wow, but they actually said, stay away from me. Because radioactive has a bad connotation to general public because of the nuclear power plant failure and also atomic bombs. So it's not me who changed those names, but the physicist. We decide to change, not change, we decide to use rare isotope, or we call it exotic nuclei. Okay, that's why exotic nuclei basically means radioactive isotopes. So I study properties of exotic nuclei, which means radioactive isotopes. Okay, so exotic nuclei, also known as radioactive isotopes, they have half-lives, so they decay somehow. They do not stay same. Some decay really fast, like a nanosecond, even shorter. Some actually live longer than the universe, age of our universe. So they decay to other nuclei by various ways. Fission basically means a breakup with 2 big chunks and the smaller neutron exit particles, or they can decay by alpha particles. or they decay to beta decay, or they decay gamma. When in mathematics, when you don't know something, we call it X, Y, Z, right? In the era of the Curie, as someone mentioned, she and others didn't know what something came out from this radioactive isotopes. That's why this alpha, beta, gamma coined. We didn't know what alpha was, we didn't know what beta was, we didn't know what gamma was. We just named it, that something came out. And then Rutherford, he got Nobel Prize by identifying alpha is actually the helium nucleus. Okay, that was a big deal. And then later, beta realized known to be electron, and gamma considered to be very high energy electromagnetic field or electromagnetic particle. We call it photon. Okay, so X-ray is a low energy photon. Gamma is the highest energy photon. Okay, so probably you already know the universe started at about 13.8 billion years. So 13.8 billion years, there was Big Bang, so where the universe started it. So how do you know, there was a Big Bang? There are three evidences. One is Hubble expansion, and another one is microwave background radiation. I'm not going to mention these two. However, if you look at the high school textbooks, they always say nuclear abundances, or we call it Big Bang nucleosynthesis. So if you understand basic principles of nuclear physics, Big Bang cannot make heavier elements heavier than helium. So all those stars considered to be first generation stars do not have anything heavier than lithium. So this was another big evidence of the universe started with a Big Bang 13.8 billion years ago. So I'm going to show you this slide a few more times in the later my talks. X-axis is the number of neutrons. Y-axis is number of protons. So we plot, there's 8, and 8 means oxygen. If you have 8 protons, that means oxygen, right? So 8 neutron makes oxygen 16. And then, so all those elements like uranium, this is lead. Lead has 82 protons and 126 neutrons. So there is something special about these numbers, like 8, 20, 28, 50, 82, 126. It actually bothered nuclear physicists for many, many years. Couldn't understand why these magic numbers are the way they are. And someone who understood theoretically got Nobel Prize, Maria Mayer and Jensen. But I'm not going to talk about them much, except there are only 300 stable isotopes. You and me are mostly consist of carbon and nitrogen that are stable isotopes. So, however, in the universe, we think there should be about 7,000 to 10,000 radioactive isotopes. So far, some of the radioactive isotopes were founded. However, not all of them were founded. However, Big Bang only can make hydrogen and helium, and all other heavy elements were made inside the stars, considered to be the core of some stars. But there are other elements, we call it the all-process path elements. We still do not know how they were created inside exploding stars like supernova and these days neutron star merger. It's actually very exciting time for astronomers and nuclear astrophysicists because we are actually at the beginning step of the new findings where the heavy elements came from. So if you think my lecture is boring and wanted to get a nap, but before you go to take a nap, these are the two things I want you to remember and make part of your new learning. Nuclear reactions in stars are very important because two reasons. One, they produce energy, and they also, second is they generate the elements. They are the key findings, important lessons that I like you to learn from my lecture today. So, mass, how much do you weigh? Mass is very important in our everyday lives, but also mass is very, very important right from the Newtonian era because gravitation, they all, if you have mass between these two, they have attractive force. However, why the mass is created at the first place, this Higgs measure, I'm not going to talk about even deeper than that, but mass in nuclear physics is also very important. This is a life and death situation because if you, this one also, you probably seen this in high school physics textbook also. If you combine all those elements, not combine, if you list all those elements from hydrogen to uranium, by the way, uranium is the heaviest natural isotope, okay? Anything heavier than uranium was man-made by accelerator or even, atomic bombs and so on. So if you measure the mass of nuclei and divide by number of protons plus neutrons. By the way, nucleon is a name to address proton or neutron. So nucleon. So number of energy divided by neutron number. Then these are the formation. What that means is the chemists always think, okay, all those noble gases are very stable. It takes the most energy to ionize them. Ionization of when the chemists indicate, that means taking the electron out. However, when you really break the element, that means you have to break the nucleus. The unit is quite different. The chemists, they say, in order to remove electron from hydrogen, you need 12.6 electron volt. Now, in nucleus, if you want to take one proton or neutron out from nucleus, usually it takes 8.5 million electron volt. The unit is like 1 million times bigger. So we are in a totally different field, different league. So when you ask nuclear physics, what is the most stable element? We say ion, because to change ion, you need the most energy. So that's the nice division between nuclear fusion versus nuclear fission. So this right-hand side is how the atomic and nuclear bomb works, and left-hand side is nuclear fusion is how the sun and the supernova and how the sun create the energy. Okay, so this is animation of uranium fission. So let me just show one more time. Neutron hits, they were stable, but small energy of neutron just even slightly touching, it breaks. That's called nuclear fission. And then if you compare the masses, somehow the uranium-235 means you have 235 nucleons, which means sum of proton and neutron. So it's actually heavier than the fission fragmentations. But the small energy difference, if you combine with, if you use the Einstein's E equal mc square, it makes a huge difference, okay? So this is how we knew that the sun works. The small differences in masses multiplied by the speed of light square makes a lot of energy differences. So again, sunlight is very important because we need it for life on Earth. So we call it thermonuclear fusion. Fusion is the energy source in stars. So mass of the nuclei after fusion is slightly less than before. So missing mass gives the kinetic energy of the other particles, and kinetic energy means temperature. Okay, so that's the whole fundamental the understanding of this thermonuclear fusion. So again, tiny difference in mass is released as energy. So even though tiny mass here, c square, speed of light, 3 times 10 to the 8 meter per second square is a huge number. So it releases large energy. I actually went to undergraduate at UCLA, and even back then, you know, the physics considered to be very difficult, 1980s. So there's even joke that the physics class is so hard, it's even difficult to find classroom. So the physicists, when we decide to make a big lecture halls for general majors, the physicists at UCLA, asked the architect and architect to make physics hall more, beautiful. You've been to physics building, I don't know, they are really dull, but they tried to make it nice. So nice arts, So physicists back then, this story I was told by my professor when I was at college. So when you look at this E equal mc square right there, I'm going to blow up picture a little bit more. It looks like this. Something odd, right? First of all, it's okay if you use a smaller letter instead of a capital E. When physicists find out that, okay, we made a nice, art, so they actually missed the 2 right there. So it said E equal mc. That's the one they put it there in a tile. So, I mean, physicists cannot accept that because the unit is even wrong. That's not the energy of energy unit. So physicists kindly asked someone who create those to put 2. He or she refused. He said, art doesn't have to be exact. So physicists actually use a letter and put 2 instead. That's why it looks a little bit odd. Okay, so we need understanding among other publics about science a little bit. Okay, this is another slide I borrowed from internet. This is how everyone sees about the nature. This is how scientists see the world. Okay, today maybe other distinguished lecture speakers will talk about other fields, but I'm only going to talk about this one, okay, how the sun works. So I'm not going to give you a typical equation except this one. This is the hardest equation that you'll see. Otherwise, you'll all go to sleep. So, okay, this one, Coulomb barrier, Coulomb potential, usually 4 pi epsilon naught, Q1, Q2 divided by 4 pi epsilon naught R is the potential, but if you can just convert this way. So this is Coulomb potential, Coulomb barrier. Also, thermal energy is always KT. Okay, so this is if you know the temperature of the equilibrium state, you can understand the thermal energy. Basically means kinetic energy of a particle. Or if you have two charged particles, you can, if you know the distance, you can understand the potential barrier, Coulomb barrier. So let's just choose arbitrary temperature, 10 to the 8 Kelvin. The surface of the sun is only 6,000 Kelvin. Inside the sun, it's even less than 10 to the 8. So, but I just wanted to make, it's actually 1.5 times 10 to the 7 Kelvin, but I want to make it even number, so 10 to the 8 Kelvin. Thermal temperature is 10 kV. Electron volt basically means you have 1 volt difference and you put a electron, then the potential difference will create the kinetic energy, and that's the 10 kilovolts. Now, deuteron, I already told you deuteron is the particle combined with the proton and neutron. They are stable actually, deuteron is stable. So deuteron plus deuteron can make helium-3 plus N. This is a nuclear reaction. Two deuterons somehow combined makes helium-3 and release the neutron. So if you think two neutrons can combine, that means they have to overcome positive repulsion, right? Because plus they repel each other. So if you use this Coulomb potential, Coulomb barrier we call it, is 400 kV. So what does it tell you? Sun would never have enough temperature to allow these two deuterons to combine. So that actually stopped the understanding of our sun for almost 50 years. Because simple electromagnetism and simple thermodynamics cannot explain how the sun works. Even though Einstein's 1905 said mass is important, mass can make everything energy great. So people thought sun being lasting that long cannot be powered by chemical reactions. So it has to have nuclear reactions. However, unless someone is very, very wrong with his temperature, everyone knew that the inside of the sun was accurately predicted. So this cannot be happening. But what's the answer? There is a quantum mechanics came to rescue. Yes, tunneling effect. So everybody was shocked. Everybody said, okay, classical physics cannot make this happening. Deuteron cannot fuse to make a helium-3 at all. However, quantum mechanics exactly predicted the probability of this happening, even though the probability is very low because the small mass change will create a lot of energy. It actually worked out really well. So that's the understanding of our sun. So the nuclear reaction in sun is, we call it PP chain now. Two protons combine to make a deuteron. Deuteron combined with the helium-3 and so on makes beryllium-6, so on and so forth. Then final product is helium-4. So our sun is the factory of helium. Helium is very expensive on Earth these days, but our sun makes helium. And by producing helium, each cycle, each time that they make a helium-4, it releases about 25 MeV energy. MeV, again, is very high energy. So this is supposed to be animation, but somehow this doesn't work. But anyway, so the reason why I'm saying is this. In the sun, nuclear physicists and theorists predicted that our sun will be powered by combination of many different nuclear reactions. Nuclear reaction is basically this. A nucleus collide with the B nucleus can create C plus D or D, E, F. So nuclear reaction basically means two nucleus collide or combine or fuse. They make another nucleus. That's the general definition of nucleus. So more correct result is this. In our sun, 4 protons using many different types of nuclear reactions produce helium-4, charge has to be conserved always. So we create two positron. That's the opposite charge of electron, okay? And then two neutrinos, and Q means the energy, okay? So, however, all these nuclear reactions were not well understood back then. So nuclear physicists tried to measure these cross-sections very actively, very precisely, especially this one, beryllium 7 plus P goes to boron 8, because boron 8, they beta decay to make electrons. So Hans Bethe, he was born in 1906. He lived almost 100 years. I even went to his lecture when I was at Caltech, but he got Nobel Prize in 1967 for his contribution to the nuclear reactions, especially the discovery concerning the energy production in stars. So he predicted that our sun is powered by this hydrogen burning. He actually called it CNO cycle, but turns out he was wrong slightly. But it wasn't his fault. Back then, we didn't know the exact temperature of our sun. But anyway, he was awarded for his pioneering work to understand the nuclear reactions that generate energy and elements in our sun. Okay, so because of what time is it now? Okay, I'm doing okay. So let me go back here. Tomorrow or sometime this week, you will hear about the dark matter and also neutrinos and so on. Okay, another interesting particle, one of the rarest fundamental particles, is this neutrino. So nuclear physicists and solar scientists who study our sun knew that this is the right reactions. However, if you are 100% sure that if you understand this is the real correct reactions, then I think one can understand this neutrino, production of these neutrinos, okay? So what people did, it was, okay, understanding our sun is very important because our sun is the closest star to Earth. If humans do not understand our own sun, how can you be sure that we could understand, other exploding stars like nova or supernova, even neutron stars? So some people thought, that's just wasting time. We already understand the nuclear power plants, nuclear reactions in stars. So they don't worry too much about these neutrino productions. However, Fowler at Caltech and Bakal at BNL, they decide to measure these neutrinos in our underground on Earth. Neutrinos, they only interact weak interaction. Weak interaction basically means they seldom interact with other metals. They only go through with a very weak decay, weak interaction. So when they measure, they measure only about 1/3 of what was predicted. And there was a big discussion. Maybe theoretical model predicts this much. Don't worry about this unit. 7.7 is what you would expect to measure. You can almost say, okay, neutrinos would measure like 7.7 events per arbitrary time. This time maybe about a month. It's not exactly 1 month, but for the sake of argument. And then what the real detection was only 1/3 of this one. So there's an error bar because, what if your theory is wrong? What if you made the wrong number for the temperature of the sun? And detector? What if your detector has certain limitation and so on? But still, there was a big discrepancy, right? So for the longest time, the people who measured this one they were under a lot of pressure. They said, 1/3 of the difference is not much. There was even paper saying, if you just keep increasing a little bit by arguing something and lowering that, they say, okay, everything is okay, no problem. But they both insisted. What we did scientifically with an error bar is what we stand. So there was a so-called solar neutrino problem for almost 30 years. Physicists and scientists do not wait that long for solving certain problems, but it was a mystery. But mystery solved. What happened was he was the one who measured the detectors. I mean, he put this. This is not a paint. This is actually a real photo. He's Ray Davis. This was the underground lab, big tank, chlorine, and tried to measure this. He measured the neutrinos and found that only 1/3 of the expected rate. And then he was the first one who actually measured neutrinos coming from the inside of our sun. So he got Nobel Prize for that. I think more importantly, he was diligent, he was insistent, he kept trying to improve his numbers. He never he just stood by his number. Okay, so turns out now, many years later, other physicists measured using different detectors, found out that the neutrinos coming from sun, they actually oscillate. They actually convert it to another neutrinos. So neutrino has 3 families: electron neutrino, muon neutrino, tau neutrino. Electron neutrino that was initially created inside the sun, while they're traveling to Earth, they convert it to muon and tau. That's why we only measure 1/3. Everything was, everything was now understood, and even theorists actually indicated that could be possible. But experimental-wise, this McDonald, he's a Canadian. He actually measured muon neutrino and tau neutrino together, and then understood the solar neutrino problem is gone. So he also got Nobel Prize. Now going back to this abundance. So I indicated that all those elements were created mostly inside the sun. This is the actual photo of a meteorite that dropped to the Earth. We call it it's a chondritic meteorite, and people analyze the abundance elements. So this is the abundance elements. So you can see there's a lot of information from this tiny, not tiny, but anyway, small rock, meteorite, came from the heaven. We analyze this. Y-axis is the abundance ratio, abundance scale in log scale. So 10/9 means 10 times difference. Okay, so this actually tells a lot about the nuclear physics as well as our sun and the universe. This actually represents the solar abundance. Okay, for example, why there's up, down, and so on? Because somehow nature favors even number. 2 is better than 1, 4 is better than 3. So all those things. And also, you can tell the lead among the mass region around here is the most abundant. That's why lead brick is very cheap compared to other copper and other things, tin. But the lead is huge. Why? Because it has 2 magic numbers. We call it doubly magic nuclei. 82 proton numbers, 126 neutron numbers. They are more stable. More stable means they don't decay. They like to stay the same. So I just did the Google, and the ratio between, the abundance ratio between iron to gold is about 1 million on Earth. And if you Google and try to check the price, gold is about 1 million times more expensive. If you find, of course, gold is precious, but even these days, diamond. Astronomers actually found out that the certain star consists of mostly diamond. Diamond is nothing but pressurized carbon, so it wasn't. So the economy somehow deals with this abundance. So again, but for a long time, see this one? Hydrogen, helium was mostly created in Big Bang, and there's a big gap here. Beryllium, boron, lithium. Why? Because they are not that stable around the mass region between 8 and 10. And all of a sudden, nitrogen, carbon, nitrogen, oxygen are very important. So people cannot understand how helium can create this carbon. So there was another huge obstacle for understanding the abundance of the elements in our body and in the universe. So famous physicist and astrophysicist Hoyle in 1953 indicated that, okay, because there are so many carbons in our body, in our universe, carbon-12 should have 0 plus excited state. This means resonance. If you have some nucleus, just like atoms, electron have excited state, right? Nucleus, when they combine with the proton and neutron, they can also have energy, then they have an excited state. Excited state basically means more energy. So carbon-12, when they are stable, they are on the ground state. When they get energy by bombarding by some other particle, first excited state is 4.4 MeV. Hoyle predicted that there should be 7.6 MeV state even before experimentalist measure actually. So he predicted this in like 4 years later at Caltech group. They actually found 7.65. So this actually, even though this is a microscopic, tiny information for some, it actually removed the major roadblock for the theory that the elements are made in stars. Hoyle is the one who didn't believe in Big Bang. So he's the one who said universe is the steady universe and that there's some crazy, he didn't say crazy, but he said there's some minor group of people who think there was a big bang many years ago. So that's why the name was coined Big Bang by him. But he was a good physicist. Okay, so in our body, by weight, mostly oxygen because of the water in our body, and carbon has 13% and hydrogen 10%. So carbon is very important. Okay, so Fowler, he got Nobel Prize in 1983 for his pioneering research. He basically said, not only saying, but he actually wrote a paper indicating major key reactions, how heavy elements were created in certain stars. Okay, so going back to my field, so I measure nuclear reaction rates, but by itself, we cannot really understand the evolution of stars or synthesis of elements. We actually need to work together with astrophysicists who do model simulation and also astronomy observations. Just to give you an example later. So again, as I indicated, y-axis is the neutron number, z-axis is the proton numbers. All these black boxes, the stable isotopes like carbon-12, carbon-13, iron-56, and so on. So Big Bang can only create hydrogen and helium, and all other heavy elements, like red giants, they call it slow neutron process, we call it S process, can create elements up to uranium and so on. However, in a supernova explosion, it can actually go very exotic nuclei reaction. So this is just predictions. We don't know yet whether it will go this way or even further down there or it even go there. So, but we call it R process, rapid neutron capture process. Considered to be the main reason why there is we have a lot of heavy elements in our universe. So in many cosmic phenomena, radioactive nuclei play an influential role, hence we need radioactive ion beams. So how do you study these reactions? So you need special facility called radioactive isotope beam accelerator. I don't know whether you are scheduled to visit around. Okay, good. Then I don't have to mention a lot about that one, okay? Because I think someone there will probably explain. So he got Nobel Prize for this one. It was a pioneering seminar paper in 1957. The title is this, Synthesis of the Elements in Stars. So he got Nobel Prize for this one. And as early as 1985, he said, we not only we need a stable accelerator, stable ion accelerator, but also we need a radioactive nuclei production by special accelerator. So one of the experiments that I've done at RIKEN, Japan is the boronate is a radioactive isotope, exciting nuclei. Before it decay, it can actually combine with another nucleus and create beryllium-7p. So boronate beam going through this certain target, in this case, lead target, I think. And because of the nuclear reaction, it breaks to proton and beryllium-7. So it's one of the important reactions to understand beryllium-7p gamma boronate reaction. Nuclear physicists like to put it this way. This is just a notation we use. Beryllium-7 combined with the proton can make boronate, but it can produce the gamma. This is one of the reaction in PP chain inside our sun. Okay, so we publish our data in Physical Review Letter back then. So this shows a cartoon of showing binary stars. Because of the gravity, this neutron star can pull this companion star, and because of the high temperature and density, it actually explode nuclear reaction. Okay, so inside that nova or X-ray burst, there are many reactions that are happening in such a short time. So how do you know which reaction happens in what temperature and how much? Okay, that is what I do, what we do as a nuclear physicist. So we give important nuclear reactions to the people who simulate this explosive stellar sites. So again, all these isotopes, blue one is stable isotopes. So if, for example, oxygen 16, 17, 18 are stable isotopes, but oxygen 14 and 15, they are radioactive isotopes, exciting nuclei. However, in the stellar sites, such as nova and X-ray burst, they don't go by this slow, stable isotope. They actually go through this radioactive isotopes. So two of the important reactions is oxygen 14 eats or fuse alpha particles and becomes neon 18, or oxygen 14 alpha gamma, or another one is oxygen 14 alpha P reaction. So that's the reaction. So again, this is the notation I already told you. For example, nuclear reaction basically means carbon 12 basically means two nuclei collide and makes another nucleus. So carbon 12 collide with proton, produce nitrogen 13. Why they need to collide? Why do you need accelerator? Because accelerating particle basically means temperature, kinetic energy. So if you want to mimic the temperature of the certain star, you have to collide them. So kinetic energy is equal to temperature. So if you want to change the temperature, you change the velocity of these accelerating particles. So that's why accelerator is very important. So if you go to the round site sometime this week, yes, you will hear more about this one. So carbon-12 collide, have a nuclear reaction with proton, can produce 13. Of course, it doesn't have to make a 13, nitrogen 13 all the time. This is the reaction that we're trying to look at. Sometimes it doesn't react, then proton just comes out and without any change of the nucleus. So usually notation is carbon-12, heavy one, we put it as a target. This is just standing there. And proton by accelerator, like a cyclotron or tandem accelerator, they produce. And you're trying to measure either gamma or nitrogen 13, then this reaction is measured. Okay. Another reaction that I just mentioned is this one. Oxygen 14 radioactive isotope combined with alpha, how much will it make fluorine 17 and proton? So this time you cannot make this oxygen 14 as a target because they are radioactive. So instead, we create this oxygen 14 beam and then hits this helium gas, then trying to measure either proton or fluorine 18 to understand if you send 100 of them or 1,000,000 of them, how much proton are created. So that's the general idea. So how do you create this radioactive isotope beam? Nitrogen 14 is a stable beam, so any decent accelerator can produce nitrogen 14 beam easily. So they are stable beam hitting this target, then they create oxygen 14 by PN reaction, with proton converting to neutron or neutron converting to proton. So this dipole, they just select only the ones we want. So all these magnets and these F2, Q2, all these things is just optics, beam optics. Q means quadruple, like focusing lens. Because of the Maxwell equations, electromagnetic fields are very well understood. So using electric force and magnetic force, we can bend any charged particles the way we want. So we send the nitrogen 14 beam hitting liquid hydrogen target. Then over here, a lot of different types of particles comes up, but we only select oxygen 14 here. And then oxygen 14 hits helium gas and trying to measure proton to see the cross sections. So this is the detector system. It may be difficult to see. There's a silicon detectors trying to understand this, but this one is about not big, 10 centimeter, about 25 centimeter. And inside there's helium and oxygen 14 goes here. So we just measure and publish the data that can modify the simulation of nova and so on. So now I'm going to switch my gear to talk a little bit about other accelerators and the research results. Before I do that, again, I'd like to remind you that night skies normally like this, but if there's a supernova exploded, then the light of supernova is more intense than all the night stars intensity combined. So this one is supernova 1986, 87, I forgot. But this actually fuse. When you take a picture of supernova itself, the background is all disappears. So actually this is taken by itself and superimposed with the background. So again, nuclear reactions in stars are very important because of the energy generation and element synthesis. Korea is very well known. Before the Republic of Korea, there was a Joseon dynasty, and this dynasty is very well known to record almost everything. How the king lives, and also heaven's movement, and so on. So every day they record everything. So if this is Chinese character, because back then, even though we have the Korean written system, I think educated people still use Chinese characters. So should I speak in Korean? If I just read this Chinese character in Korean, 야유일경, 객성재미숙, 10도 거극, 110도 체형소, I forgot Chinese character, 소세, 성색황적 동요 오경, something like that. Okay, basically means this day there was some guest star appear, and XY. Korea had our own, the positioning information, X and Y, and it says it moved a little bit because they think it actually moved because of the explosion, I guess, but it didn't really move. And they compared it became like bluish, and compared with the other known ones. But they say in early in the morning, because of the cloud, cannot see. So every day it recorded it. Like even November 22nd, they said because of thick cloud, cannot see the guest star, supernova. Okay, so when the observation was, they always compare the brightness with the known, currently known planets like Mercury and others, and combined with the days after the explosion and also magnitude of the light. So this is actually famous Kepler supernova. So if you compare this European observation versus Korean observation was more informative, first critical 2 months or so. So this was published in a very good journal, I think either Nature or Science, I forgot. So what's happening inside of supernova? Somehow this simulation doesn't work in this particular notebook that I put this presentation file, but within like 3 seconds, everything explode, and all those eye process seem to happen. So without showing actual simulations, again, I just want to remind you that there were 11 greatest unanswered questions of physics compiled by physicists about many years ago. I forgot, this one was about 20 years ago. And one of the 11 questions, the ordering is not important. We still do not know where were the elements from iron to uranium made. We have some ideas. So as I mentioned, supernova collapse can create all this I'll process. So it's happening. Iron is the most stable. So from here it's creating this. Okay, it's keep going, keep going. So all this called I'll process, and all of a sudden it happens. It only happens in less than 100 seconds in this case, but most of it happens in less than 1 second. Another possibility is neutron star merger. So I want you to look at this. 2 neutrons, they merge. Neutron stars actually the remnants of, not remnant, the leftover after supernova. If it doesn't become black hole, it becomes neutron star, okay? So neutron star can merge, they can actually produce heavy elements also. So at this time, people think supernova explosion combined with the neutron star merger are the reasons why in our body we have lead and other heavy elements. We can only understand 50% of the element synthesis, so-called S process. R process, I can almost say we don't know anything yet, but these are the predictions. So all these paths, I'm just going to show you this again, are just a simulation based on theoretical models. Some nuclear reactions are not well understood yet. So that's why we're trying to measure this one. Okay. And radioactive isotopes, very important. So there are many so-called second generation or third generation radioactive ion beam facilities in the world. One of the most important, well advanced and most productive one at this time is the RIKEN in Japan. They produced 150 new isotopes. It tops in the 21st century. Before, GSI in Germany and also Russia and United States actually used to produce many new isotopes, radioactive isotopes. And again, nature has the magic number. They actually did some exotic nuclei structures and found out that the existing magic numbers no longer apply to some of the exotic nuclei. And also, the group at RIKEN actually found new element, new chemical element, element number 113. That's the first by Asian country. And also, physics with exotic nuclei. See, the reason why you want to have more exotic nuclei is to understand R process path to synthesize up to uranium. So these are one of the key reasons why we want to have exotic nuclei beams. We call it RI beam or rare isotope beams. Okay. What about the United States? Michigan State University recently finished building this very nice accelerator, the facility for radioactive rare isotope beam. This is a huge facility funded by U.S. Department of Energy, and it will be very competitive. Accelerator is like a huge microscope to understand the fundamental properties of small particles like exotic nuclei, and also understand the R process reactions. What about Korea? We are here, Daejeon. Daejeon is almost the center of South Korea. Now, if you blow up this Daejeon region, we are here, IBS, and this scale is like legend is 3 kilometers. So there's a round Korean accelerator site. It takes about 25 minutes by car. So if you go there, you will see something like this. But round is the name of the accelerator that's being built in Korea, owned by IBS. So IBS is part of, this round is part of IBS. The main goal is to build a heavy ion accelerator complex, usually for rare isotope science. So it's $1.3 billion. It already started 10 years ago. We'll finish first phase of accelerator sometime this year. And then second phase will be constructed later years. So this is a photo taken by drone. So when you go there, you'll see all this one. But this red one indicates accelerators, experimental systems, low energy experimental holes, and high energy holes, and also some conventional utilities. the area is actually bigger than the campus of IBS. It's a huge. It's a very nice place. It's close to 1 million square meters. So in there, there's 3 different ways of producing RI beams. Okay, one is this. I'm not going to talk too much in detail because you will be informed later. Another way is so-called isol way. And then in the future, we're going to combine isol with SCL2, superconductor linear is what SCL means. So this is the RIB, radioactive isotope beam or rare isotope beam production at round. So you can produce by COBRA. COBRA is the low energy experimental facility that can produce RI beams, or you can produce RI beam by ISOL, or you can produce by IF, combining ISOL with IF. Okay, again, argon is the forefront of this radioactive isotope accelerator, but the FRIP just came along, and there's a TRIUMPH in Canada, ISOLDE in Europe, and also there's a GSI in Germany, and Ganil in France, and some also there are the ones in China, very active ones. So I talked about 70 minutes. In the last 5 to 10 minutes, I will wrap up, briefly showing what kind of experiments we have done and will be done. So this is too much detail, so I'll skip. You should thank me. And also, we are developing some of the state-of-art detector systems using silicon detectors and germanium detectors and so on. You know what? This is a high-purity germanium detector. This is very expensive. This costs as much as a small house in Korea. Yeah. And also the silicon system and so on. So I skip this because in order to measure nuclei, you need special detectors. I was going to bring some detector today, but somehow it doesn't work with the live YouTube scheme. So again, chart of nuclei, just trying to tell you many different reactions can be used to understand the stellar evolution of stars and also the energy generation in stars like nova, X-ray burst, and supernova. One of the exciting discovery that was just announced about last year is we actually found the evidence of tetraneutron. So tetraneutron was discovered with smaller error bars by groups here, and this was published in Nature. So using helium-8 radioactive isotope beams, hitting proton, then we actually detected this helium-4 and proton. So because we detected this, what's left was this 4N, and they didn't break up. They were there. There was an evidence with certain error bars. So this was very exciting. So we said, okay, there's a 4N system. However, as I told you, nature favors 2. Why not 2 neutron? Well, we didn't discover. 3 neutron didn't discover. All of a sudden, 4 neutron system was discovered. So you can read about this one. So there was the resonance here. Very clear indication there was something there. So now you can rest. I'm going to quickly show there's something I like you to know. You are here to understand new science and principles, but I want you to think about what is nature of science. Scientists like me, we don't usually ask this question. We just do science. But many important great minds ask, what is the nature of science? For example, they are great philosophers and also some scientists. Okay, so there's a school of thoughts, inductivism. Bacon actually played a very important role to shape the early scientists thinking, how scientists work. Popper, Kuhn is also very famous, and so on. But let me just give you this. Popper was known to say, theories come from anywhere. No theories cannot be proven correct. Because single right experiment can show a theory is false. So he clearly indicated that to understand the nature, you can have many different theories, that you cannot prove the theory is correct forever. However, we all know theory of relativity is considered to be fact. But what he's saying is experiments are very important because there may be something different experiment or different observation that disproves your theory is wrong. Okay, and also Kuhn, he was actually high energy physicist. By studying the physics, he realized what the previous philosopher of science, what the science is, he think is the wrong. So he said there's a normal science. Then sometimes he's some anomalies that cannot explain the anomaly. Then there's a real crisis, and then they call revolution and comes back, something like this. So it was very well accepted in many ways because the evolution of theory of relativity and evolution of quantum physics, even Kepler and had very strong objections. So he also claimed scientific community is very important. So sometimes, you need to be approved by your science communities. So even good scientists have a lot of difficulties in certain cases. But just give you a good example of science because there's a bad sciences also. Okay, but good science. Okay, there was some very nice paper by indicating, there could be another force, fifth force. So it was published in one of the well-respected journal in physics, Physical Review Letter. And then a few years later, see, there's no evidence. So they actually say, okay, we made a mistake, sorry. Okay, so they were good scientists. We all make a mistake. So this is a good example of how you do science. But you all make mistake. Even Einstein, after he published the general relativity, first few times he said, okay, don't read my papers, I made a mistake. So, but at that time, no one understood anyway, so he just kept changing. So he's considered to be the great scientist. We all make mistakes. So observation, do you believe everything you see? So in old school of thought was observation is very important, but even sometimes observation can be depending on the situations. So you see what you want to see. You believe what you want to see. Sometimes I even always trying to be objective, but you see dots in the middle, but there's no dots. What about this one? It's circling? No, it's not circling. Do you see two different boxes, right? Red in front or blue in front? This could be what? Two different animals? What? Exactly same thing, but depends on the contact. They look different. So scientists, sometimes we overlook something, and there's a famous decay, we call it zero neutrino decay. If there's a peak right there, if everyone believed there was a peak, then he or he could get Nobel Prize. So this person, they published a paper saying, okay, we find the peak. Okay, but no one believed that. But you all know the story, right? Michelson-Morley experiment. They actually thought they failed to see the ether, the medium that the mediate the light. And Michael and Morley said, okay, we did this much, but couldn't see the ether. So he actually was very sad. He said, but he published the result. Using this precise, we didn't see ether. So he himself really considered that he didn't find ether, because back then, all those waves should have a medium. You know, my voice to you can be connected because of the air and so on. So all those waves need to have some medium. Ether considered to be must, but they said we couldn't find ether. But it was one of the most successful experiments in physics. Got Nobel Prize actually for this one. So again, I like to emphasize Madame Curie, because someone mentioned. She was awarded Nobel Prize twice, one in physics, one in chemistry. And you could almost say, like, the way she wrote this one, you'd think she was like a general worker, but according to Einstein, she's, of all the celebrated beings, the only one whom fame has not corrupted. Because if you go to hospitals, there's radioactive isotopes to cure disease or even diagnostic purposes, right? She could make more money than Nobel Dynamite. But she didn't want to patent her discoveries, because it belongs to nature and belongs to the humankind and not to her. So that's where her mind was, because to understand nature is what's most important. So I just want to end my talk by saying I know you all came here for Asian Science Camp, and you are interested in science and learning new things. You can always be the best you can be. But there's something special about science and being scientist. If you want to be a scientist or anything you want to be, it's not easy. But if you want to be successful in your field, you do your best, and you can meet another best in other fields more easily than any other ways. Okay, so again, this is a Fowler. This is Gamow, who actually predicted there should be a Big Bang, nuclear synthesis in the early universe. And Carl Sagan, okay, he said we are all made of stardust that were created by nuclear reactions. So I want you to know that the universe is full of magical things, patiently waiting for our wish to grow sharper, because there are still many unknowns. During all the lectures this week, you would think that, we have so much knowledge about this and that, and aging, and DNA, and virus, and all those things. We still don't know many things. So we need young minds like you to explore the unknowns, because there are so many unknowns in our universe. So thank you so much for your attention. Okay, thank you.
Well, now are we ready to accept some questions from the floor? So we will be accepting from the floor first, and then go to Zoom to accept questions from the online participants. So, dear participants offline, if you raise your hand, we're going to, yes, the participant at the back, please stand and introduce yourself and your question as well.
Hello, I am Seongyu, and I'm from Korea, and I'm currently a freshman in a university. and I would like to ask you, what did you learn during your undergraduate life, and what did you learn more in your graduate life?
Yes, I went to UCLA, as I said during my lecture. It's a big university, so I majored in physics, as you probably guessed. Unlike Korean university, we didn't have to take a lot of physics courses. Instead, we are encouraged to take liberal arts class and other fields. So I only took 1.5 physics courses per semester. Actually, we had a quota system. So, but we had a lot of experiments, lab courses. So that really helped me to go to experimental physics. So I think we just basically cover E&M, thermodynamics and classical mechanics and so on. And then I only took nuclear physics and particle physics. I didn't take any solid state upper classes. However, when I decided to go to graduate school, in graduate school, everything is physics course. So first 2 years are very, very difficult. A lot of pressure, many difficult problems, homeworks. So what I really learned about physics came from graduate courses, not undergraduate, but undergraduate courses are still important because without those, you cannot understand graduate courses. Does that answer your question? Yeah.
Why did you choose this field to study and research?
Okay. That's a very good question. I was really good in math, even in high school. My family immigrated to United States when I was junior in high school. So I did it very well in math, and then I wanted to go to science. So for me, it's a choice among physics, chemistry, and biology. But I thought physics is the basis of all sciences. And because math is the language of physics, so I thought I would be good at physics. However, I wasn't sure whether I would be very successful in physics. So I actually applied engineering in graduate school, and I was accepted in some of the graduate schools. But at the end, it was real struggle among inside. But I really couldn't take any other subject besides physics. But yes.
Yes, that was some of the background story or personal story, how he has now ended up doing research related. And now we'll be accepting one more question from the floor. So if you raise your hand really quick, yes, please stand and present your question to the director.
Hi, my name is Yu Chen Shin. I'm from South Korea, and I have a question related to nucleosynthesis. So, whenever I was studying nuclear chemistry, I always had this question. Iron does indeed have the highest, binding energy per nucleon, which theoretically means that, elements that are lighter or heavier than iron should, converge to being iron. So my question is, why don't we see many more, iron? Like, why isn't iron much more prevalent in the universe? And, theoretically speaking, as time passes, will we even see, complete stars made out of iron as, they reach the end of their nucleosynthesis?
Okay, very good question. Okay, his question is, iron is considered to be most stable nucleus. Then most stable means you have to stop right there because nature wanted to be stable as possible. The reason why iron doesn't stop there instead of making heavier elements is because of the temperature in the high temperature and high density in certain stars, not all the stars, like only in supernova and neutron merger. If ion is there, we can still make heavier ones by bombarding protons and alphas. Why? Because nuclear forces, they like to accept some of the more protons and neutrons. So that's just fact. So you can actually fuse two ions, make even heavier ones. So probability is very low. However, the asymptotic, the normal stars, their life ends when all the fuel is exist. So the core, when other stars, the ions, when ion is made, then that's the death of the star. Until that time, it doesn't make any heavier element than ion. So there are various types of stars have different path of their life cycles. So stars heavier than our sun, they go through different paths, can produce heavier elements than ion, and others they just sort of like dies out with a white dwarf and stay until making ion. The why supernova explode? Because the mass is huge, so when they burn all those elements, the ion core, all those stars actually, they are fighting with a nuclear reaction that's producing kinetic energy from outward, and then gravity inward. They are actually equally well, very finely equalized. So when there's no more energy left to produce heavier than ion, then what happens? Gravity actually pulls down, and then because of it collapses, that creates a lot of high energy. That's why ion now start capturing these neutrons, making our process and making more heavy elements. But not all those ions go to uranium and heavier. Most of them actually stay there because of the probabilities. Very, very important and good question. Thank you.
Yes, thank you very much. Now we're going to turn to Zoom in order to find out what kind of questions the online participants have. If you have any questions, please click the raise hand button so that we'll know that you have a questions. So online participants, if you're ready to give some questions, please click the raise hand button and let us know that you have a question. And as you have pressed the icon, we will make sure that your face is seen on the screen, that you'll be able to deliver the question to the director in person, which means through the screen. Yes, do we have... Okay, I can guess that there is a large crowd right there watching our lecture.
Thank you for the time. My name is Andi Setiawan, and as you can see here, I'm from Indonesia. First of all, thank you for your wonderful lecture, Mr. Kevin. And I have a quite simple question for you. So nowadays, we have solar cells and solar panels that capture the energy of the sun and convert it into electricity, right? But we have not been able to maximize the usage of the sun's energy yet. Is it possible in the future to maximize the usage of all the energy in the universe? That's it. That is my question. Thank you.
I didn't really understand your question 100%. You mentioned about the solar energy and the energy created by the sun. And can you repeat the question one more time? You are muted.
So my question is it possible in the future that we can maximize all the energy usage of the universe for example of this, the sun's energy, we can use it. We can convert it into electricity using the solar cells or solar panels, right? But it's not really efficient yet. It's not like 100% we maximize the energy from the sun. So back to my question, is it possible in the future that we can maximize all the energy from the universe to our benefit?
Okay, yeah. Whether we can maximize our energy from the universe like a sun is very difficult. Also, the terminology maximum depends on what materials and so on. For example, the way you store energy from our sun is a photoelectric effect. For example, that's one thing. There is a efficiency of some of the detectors. So solar panel technology improved considerably, but we don't know when the maximum efficiency can be made. It actually falls down to the engineering and technology. However, what I think we humans should do is trying to be successful in hot fusion technology. That's very difficult, but a lot of efforts have been put into it. For example, ITER, trying to mimic the sun, create fusion energy. I think that's the way we should go, because all the energies coming from the sun cannot be maximized, because there's always reflection and diffraction and other problems. So, but the human to be survive, live longer than like dinosaur, the nuclear fusion has to be successful. But that may not be come easily because there's a lot of obstacles. So I hope it answered some of your inquiries. Yeah, very intriguing question, but to be honest, I don't know the right answer for your question.
Okay, thank you very much. The time is up for the lecture number 2. So let us give another big round of applause to Director Kevin In-shik Khan for his inspiring lecture today. Thank you very much. Thank you very much. And now we're going to have a short break, and then we'll come back to lecture 3 at 4 p.m. Korean Standard Time. So make sure that you be here with us before time, and I'll see you at 4 o'clock Korean Standard Time. Thank you very much.
사회와 영어를 너무 잘하셔서 제가 완전 반했어요.
감사합니다.
네네, 갈아드릴게요. 말하기
Yes, as we are to begin the next lecture, may I ask all the participants to now take their seats? Yes. Please wrap up. We'll have to let the director go. Yeah, this will be the last picture together, so if you want to join them, please go ahead. This is your last chance. And now we're ready to begin our lecture number 3, who won the Nobel Prize in 2001 in physiology or medicine. He is a professor of Okinawa. Let's welcome Tim Hunt from the Institute of Science and Technology Graduate University, who is going to give us the lessons from a life in science through the screen. Please give him a big round of applause.
Hello everybody. So here goes. I'm going to tell you the story of my life, that is to say my scientific life. Starting at the beginning, I started to do my PhD in a lab in Cambridge in the biochemistry department in 1964. And my supervisor, I said, what am I going to work on? And he said, well, Tim, why don't you go to the library and find yourself a project? So I went to the library, and after about a week, I found a very nice project, which I think, fortunately for me, absolutely did not work. So for the first 6 months or so of my PhD, absolutely nothing happened, except that I sort of learnt my way around the lab, which was okay. And the key moment, really, where my scientific career could be said to start was when I went to my first scientific meeting. It was only about a quarter of a mile away in the chemistry department, and it was a meeting devoted to hemoglobin, the stuff that makes your blood red and carries the oxygen around your veins. And I heard 2 talks there that made a deep impression on me, and in fact set almost, I could say, the course of my research for the rest of my life. So the first talk was by a man called Henry Borsuk, who came from Caltech, and he'd worked on 2 very unrelated things. One was sea urchin eggs, and the other was the role of iron in hemoglobin synthesis. Heme, that carries the oxygen, contains iron, and it turned out that if you starve the cells that are making hemoglobin of iron, they stop making the protein globin. So that was the first talk. He also introduced me to sea urchin eggs, and sea urchin eggs, he described, make almost no proteins when they're just sitting there unfertilized, but the minute they're fertilized they activate protein synthesis, and that's very important even for the very first division. They don't go anywhere unless they can make new proteins. That sort of made sense. And the second talk was by a man called Vernon Ingram, and he was also studying the question of the coordination of heme and globin synthesis. And I think it'd be a good idea to show you what that looks like. So here is John Kendrew looking at his model of myoglobin, and as you can see, the protein curls its way around and makes a little fold where the heme slots in. And Vernon's problem basically was how does the heme, when does the heme go in and how does it control protein synthesis? And he presented some very interesting data which suggested that the ribosomes which are making the protein globin go along the messenger RNA until they reach the place where the heme should come in. And if there is no heme, they simply wait there and form a queue behind the service point where the heme ought to be inserted until the heme comes in. If the heme comes in, then they can go on and finish making the chain. So this was a remarkable mechanism, very easy to understand, difficult to envisage how it might actually work. And I went back to tell my friends in the lab about this amazing talk that I'd heard, and my colleagues pointed out that actually the evidence presented exactly contradicted his own theory. He'd misinterpreted his data, basically. And so we decided, and this is something I really can't understand how we had the courage to do it, we decided to check it out for ourselves. And when I say we, there were really two key people. You'll see that this talk is really mostly about people. The first was on the right, Lou Reichart, who is a very distinguished neurobiologist these days, but he started out his PhD in Cambridge and he shared the bay with me, and he in fact was trying to study the coordination of heme and globin synthesis, and like me with his first project, failed completely. I don't know why. I think it may be heme is rather difficult to dissolve, and maybe he didn't succeed in dissolving it. And the other person on the left is Tony Hunter, and in the background are reticulocytes, the cells that actually make hemoglobin. And later on it turned out that it's very easy to make a cell-free preparation simply by suspending the cells that are making hemoglobin in water, distilled water, which bursts open the cells by osmosis, and you get a beautiful deep red supernatant which will make hemoglobin. Even though there are no more cells involved, you have to add a source of ATP, an energy generating system. But that's all you have to do, and it works extremely well. And you can buy this as a kit. We used to make our own. In those days you couldn't buy it. But Lou knew how to make it, and that was great. So off we set. Tony Hunter and I really did our PhD together, and we found that actually the ribosomes did not form queues. The whole thing was a complete nonsense. And then a very important thing happened. I went to my second scientific meeting. This was in the spring of 1966, and it wasn't a quarter of a mile down the road. It was in northern Greece. And there I ran into a man who became a great friend and mentor to me, and I actually spent the summer in his lab in New York and then went back to do a postdoc. And on the right-hand side is shown the kind of thing that we could do with this cell-free preparation. That is to say, we took samples at timed intervals and measured protein synthesis. And as you can see, if you add heme, protein synthesis carries on at a nice high rate. In fact, it's pretty much the same rate as they would have been if you hadn't broken the cells open. But if you leave out the heme, then protein synthesis starts off all right. You make a little bit of globin and then it suddenly cuts out and goes to a new low level, typically 10% or something like that. If you add back the heme, it starts up again. So we have a reversible control mechanism, and we would love to understand what that control mechanism is. So I spent about 2.5 years in New York trying to work it out, but actually it was deeply unsuccessful because we didn't know enough about how protein synthesis was controlled at the time. We really were completely ignorant, and we kept on doing this same experiment, which always worked. It was extremely reproducible, but it didn't lead anywhere to any sort of fundamental understanding of the problem. And I did find out one or two of things while I was a postdoc, but they were sort of secret projects at night. And the most important one was done with a collaborator in the cell biology department at Einstein. One of the nice things about Einstein was it was very easy to collaborate, and people liked to do it. And so I found somebody who was working on poliovirus, and we discovered that tiny, tiny amounts of double-stranded RNA, which is the replicative form of poliovirus, inhibited protein synthesis in these reticulocyte lysates in exactly the same way that leaving out the heme did. And that was very, very strange, because chemically there's absolutely nothing in common between double-stranded RNA and heme. And remarkably, perhaps the most important thing was that when you worked out how much double-stranded RNA would inhibit synthesis by how many ribosomes, it turned out that one double-stranded RNA molecule could inhibit something like 10 million ribosomes. And that immediately said that whatever this inhibition was, it must be catalytic, because the trigger is vastly amplified when it comes to its final effect. But we had no idea how it worked. And so after that, I went back to Cambridge, where I joined forces with a man who died recently, a couple of years older than me, called Richard Jackson. And Jim Watson, in one of his books, says that one of the great tricks about being a good scientist is always to work with somebody who's cleverer than you are. And I think that's excellent advice, and that's what I did. Richard was an extremely, extremely deep and careful thinker. I was a little more slapdash, and between us we made, I think, a very good team. And it was we worked together for about 20 years, in fact, and it was an enormous pleasure, the two of us together. So what did we find? Well, we didn't find this. Somebody else discovered the fact that when you left out the heme, what happened was that an inhibitor of protein synthesis formed, and that inhibitor stopped ribosomes translating the messenger RNA. In fact, they stopped the ribosomes from going on to the messenger RNA in the first place. So all the polysomes, which are messenger RNA covered with ribosomes, disappeared, and you got a huge increase in single ribosomes unattached to messenger RNA, not making globin. Now, while I was in America, Richard and Tony Hunter, who I've already mentioned, discovered a very important thing, which is the way you start protein synthesis is with a special initiator tRNA carrying methionine. And so we started looking, using methionine as a label. It's a very nice label because S35 is nice and radioactive, and it's cheap and easy to make. And actually, we at one point actually made our own. And a graduate student called Chris Darnborough discovered that when you left out the heme, or when you added double-stranded RNA, there was a mysterious complex which wasn't a full ribosome, it was half the ribosome went away, and that complex went away before protein synthesis itself shut off, so that we knew that this complex was probably a complex of initiated tRNA, which then led us to realize that what happened, the way you start up protein synthesis, is by the small ribosomal subunit getting charged with initiated tRNA, and that binds to the messenger RNAs and goes along looking for the start of the messenger RNA, looking for the first methionine codon in the messenger RNA. And if you can't form that complex, of course, you can't start protein synthesis. And so the disappearance of this complex provided a very nice reason for why protein synthesis stopped. But we had a hard time publishing it because everybody knew that transfer RNA only binds to messenger RNA when the messenger RNA instructs it. The idea that the tRNA anticodon could select the start of the messenger RNA was completely the wrong way round for everybody. I mean, in other words, they said that we didn't understand anything about how protein synthesis worked, but actually we understood it better. And it's always been my experience that if you find out something that goes against the current dogma, you always have a much harder time publishing it, and you better be very sure that you're right. So that's a good thing. Anyway, so that was, in a way, the first really, really important result that I shared in with my colleagues. And then a very fortunate thing happened, which was that the lab burned down. And I got a phone call at about 7 o'clock on a Saturday morning from Richard saying, "Tim, the lab has burned down. Don't bother to come in because there's nothing left." So, of course, I immediately got dressed and rushed in. And indeed, as this photograph shows, the lab had been completely destroyed by fire, except that the liquid nitrogen refrigerator where we kept our most precious samples was still venting nitrogen, which meant that the interior was still at minus 100 and whatever it is, 180 degrees Celsius. And so the precious samples were still safe, and all we had to do was find a new refrigerator which hadn't blown its seal, and that was very fortunate, so that we were able to get back and in business in about 6 weeks. We had a wonderful story to tell. The lab has burned down. Can you get us a new this or new that and a new the other? And we had a new lab to go to. It was a teaching lab in the hematology department, opposite the famous laboratory of molecular biology, where they have, I think, 20, 25 Nobel laureates sitting there. So it was a really wonderful opportunity, and actually, at the time, we were deeply puzzled. We had lots of sort of results that didn't really make much sense, and it was really rather a good thing to burn them all up and have no possibility of consulting what they were. We sort of it was good. And more importantly, we had new neighbors, new labs, all new equipment, thanks to the fire. And Max Perutz, who was then the director of the lab, was extremely kind and said we could use his stores and perhaps more importantly, use his tea room. And the tea room was full of the great and the good of modern molecular biology. And our hero at the time, I suppose, my generation, was Francis Crick, who seemed to know and understand everything. He left Cambridge about a year or two later, much to everyone's sorrow. But not only was there Francis Crick there was also Fred Sanger, who won 2 Nobel Prizes and figured out how to sequence DNA, Max Perutz himself, who worked out the structure of hemoglobin, Sidney Brenner. And not only were there these great pioneers, but there were also a lot of youngsters, people like me, who would become in future Nobel laureates. And the interesting thing about that was that we didn't really consider ourselves to be in anything like the same league as these giants of molecular biology. We just sort of were studying interesting things and were interested in what each other were doing, made suggestions, made criticisms. And in that sense, sort of science is really very easy. All you have to do is to find a good problem and work on it and put one foot in front of the other and you solve it. But actually the reality is that it's very, very slow, and usually things don't work, and most of your time is spent troubleshooting. But it was a very stimulating environment. We were rather sorry when the old lab was rebuilt and we had to go back downtown again. But in the course of doing that, and I think it was largely as a result of making this move, we actually solved the problem and discovered this inhibitor of protein synthesis was an enzyme called a protein kinase, an enzyme that sticks phosphates onto other proteins. And the protein that it stuck a phosphate onto was an initiation factor, the initiation factor that indeed bound initiated tRNA to the small ribosomal subunit. So that was very good, very satisfactory, and we sort of thought in retrospect why were we so slow to think of that as a possibility. And we found that not only did leaving out the heme cause the phosphorylation of this initiation factor, but also adding minute amounts of double-stranded RNA had the same effect. And we now know, actually, after many more years of detailed research, that there are 4 of these enzymes, all of them sensitive to different things. So there's the heme-regulated protein kinase, there's the double-stranded RNA regulated protein kinase, which actually is a very important part of the antiviral response. There's something that responds to starvation for amino acids. And there's something called the unfolded protein response, which responds to when a cell can't fold up the proteins it's making rapidly enough, it switches off protein synthesis so that the folding can catch up. But that was way in the future, and we weren't to know that. So, but an interesting thing now happened, which was that in a way we've solved our problem, so we don't have a problem to work on anymore. So what do you do? And I remembered that talk from Borsuk about the sea urchin eggs, and I wondered what was known about the control of protein synthesis in sea urchin eggs. So I invited Tom Humphreys to a meeting that we organized, which was devoted to the control of protein synthesis in Cambridge. And Tom came all the way from Hawaii, and it turned out, I didn't know this before because I'd never met him, that he was a very keen cyclist and he wanted to rent a bicycle. And in those days you couldn't rent a bicycle, so I simply lent him my bicycle, and on that basis we became friends. And what I also didn't know was that he was the director of a course in Woods Hole, the embryology course, and he said, would I like to come and teach next year in the embryology course in Woods Hole, and maybe we could do some experiments together on the control of protein synthesis in sea urchin eggs. So I leapt at the chance, and next summer indeed I went to Woods Hole and we started working on sea urchin eggs. We didn't find out very much that first summer, but I did find out how to get sea urchin eggs, and I learned that you can't easily tell male sea urchins from female sea urchins, because all they do is shed their gametes into the sea, and they don't need to get together in order to fertilize each other's eggs. But there are males and females, roughly equal numbers, and you can find out which is which by stimulating them with a little electric shock, and that causes them to ejaculate their sperm if they're male, or lay their eggs if they're female. And if you mix the two together, this movie shows what happens after fertilization, namely that after about an hour the fertilized egg divides in 2. It's really very beautiful. And I was fascinated by that, and also learned that if you inhibit protein synthesis, they don't divide in 2. They will synthesize the first round of DNA, but they fail to divide. And it was true what Borsuk had said. There was a big increase in the rate of protein synthesis after fertilization. So this is pretty interesting. So at least one or more of the newly made proteins must be involved in catalyzing cell division. But we made no progress whatsoever in any of these things that first summer, and my recollection is we spent an awful lot of time chatting in the pub late at night, and sometimes going dancing. But the second summer I went back, now much better armed with the things you needed to do proper experiments in a funny place like Woods Hole, I ran into 2 other people, Eric Rosenthal and Joan Ruderman, and they'd been working on clams and discovered that when clam eggs are fertilized, there's no big increase in the rate of protein synthesis, but more importantly, the clam eggs start making new proteins. And this slide shows that new proteins A, B, and C are synthesized very strongly after fertilization. And another amazing thing happens after the clam eggs are fertilized. They undergo a huge change in their structure. The nucleus, which is very prominent in the unfertilized eggs, breaks down, and they form the first meiotic spindle, which is then followed by the second meiotic spindle. And again, if you inhibit protein synthesis, things start going wrong, and the clam eggs also don't divide. So I began to be interested in the relationship between protein synthesis, new protein synthesis, and cell division, because we didn't know what proteins A, B, and C, the newly synthesized ones, did. And, but they were so prominent that it rather looked like they were probably rather important. And that same summer when we were studying A, B, and C in clams, there was a seminar from a man called John Gerhardt, a very distinguished enzymologist who'd now become interested in something else, which was the maturation of frog eggs. Actually, the maturation of frog oocytes. Now, a frog oocyte is the cell inside a female frog that will become an egg when she lays it. And actually, the maturation is something that normally happens in response to the sex hormone progesterone. And it takes place over the space of a few hours as the oocytes go down the oviduct to emerge outside the female frog to get fertilized by the male frog, who is generally clasping the female frog. And they don't really ejaculate, they kind of dribble their sperm over the eggs as they come out. And again, the movie shows that when you fertilize these, when you add progesterone to these oocytes, a white spot forms in the middle of the black part. And if you look underneath the white spot, what you find is that there is a second meiotic spindle with chromosomes lined up on this array of microtubules. And what Gerhardt described was the existence of this interesting factor called maturation promoting factor, usually known as MPF, which appeared to be the substance that actually is the cause of this change in the oocytes, and the nucleus again breaks down and this spindle forms. And a Japanese researcher called Yoshio Mazui had discovered the existence of MPF by a very simple assay. He took a mature egg with its spindle and injected that back into an oocyte, and the oocyte responded very rapidly now by undergoing maturation, and didn't require any new protein synthesis, whereas the first maturation triggered by progesterone did. So there were again sort of correlations between protein synthesis and cell cycle transitions. And Gerhardt had been trying to purify MPF to find out what it was, and what he discovered was that it was very unstable stuff, very difficult to get hold of, and he really didn't know what it was. But it looked like it was important. And since he gave that talk, several other facts emerged about it, which was that not only was this found in frog eggs when they matured, but it was also found in starfish oocytes, and later on in yeast, and indeed even in human cells. So this was a substance which apparently would trigger entry into meiosis or mitosis in any cell that you cared to inject it into, and it looked like it was the enzyme that catalyzed cell division. So I thought this was a wonderful project, and began to think about that and the correlation between protein synthesis and cell division. And later on, Gerhardt did, together with Mark Kirschner and his wonderful technician Mike Wu, who I met one summer in Berkeley, they discovered that MPF levels were always high when the cells were dividing and always low in between when they were synthesizing DNA, replicating their genomes. And as I say, this wasn't just something confined to frogs. You found it all over. So I began to think, and we began to wonder, can you detect MPF in sea urchin eggs by any chance? And we even discussed the possibility of doing experiments to detect that, and never carried them out. Sea urchin eggs are very much more difficult. They're much smaller than frog eggs, so never got around to it. But then 2 or 3 summers later, I did an experiment which gave the game away, and it's shown on this slide here. This is actually the second experiment, which worked a little bit better than the first experiment. And it's a very simple experiment. You just add S35 methionine to sea urchin eggs and fertilize them and take samples every 10 minutes. Now I was looking for something completely different. I was looking for changes in the pattern of protein synthesis between properly fertilized eggs and parthenogenetically activated eggs. You can get sea urchin eggs to develop just by adding a calcium ionophore, dilute soap solutions, and various other tricks that have been discovered many years before. And I was curious about whether properly fertilized eggs made different proteins from these artificially activated eggs. Did the experiment, and to my astonishment saw that the most abundantly synthesized protein early on after fertilization disappeared just before the eggs divided. We later found out that it actually disappears just before the chromosomes come apart at the culmination of mitosis. And then it came back again, and then it disappeared again. And this was quite remarkable. Later that summer we had a look in clam eggs, and we found, and it's much easier to see in this slide here, that the proteins A and B, which are both translationally regulated, are these proteins which I call cyclins, because number one, I was a keen cyclist at the time, and number two, they cycle with the cell cycle. And the important thing is that they disappear and they come back. And if you stop them coming back by inhibiting protein synthesis, then the eggs don't divide. So it very much looks as though these are somehow intimately connected with MPF. I mean, we didn't really expect it to be MPF itself. We thought more likely it was perhaps an interconverting enzyme that gave rise to MPF. So I suddenly realized that I had stumbled on the secret of cell division, and I knew nothing about cell division or the cell cycle, so I had to I had to start reading and talking to people about that. And DNA really is at the heart of this business. Sidney Brenner, when he saw the famous Watson and Crick model, said that DNA, it was a moment of absolute enlightenment, the reduction of biology to one dimension, because he realized that here in DNA was the equivalent of von Neumann's tape. Von Neumann was a very important computer scientist who talked about the problem of inventing automata, which self-replicating automata, and he realized that you had to have an instructional tape, but he also realized that the instructional tape had to be made by the automaton. So the automaton had to be able to make a new copy of the tape and be able to insert it into a new version of itself, so that the new version of itself would continue this process. And that's what life is all about, and that's really what DNA is all about. It's just the instructions. I mean, if you're a human being, it's all the instructions you need to make a human being. Or if you're an earthworm, to make an earthworm, or a bacterium to make a bacterium. We all use DNA in exactly the same way. And the key to putting a new copy of DNA in every single cell in your body is the cell cycle. Basically, what you have to do is you first have to copy the copy of the DNA that you've inherited, to make two copies of it, and then you have to distribute those copies to the two daughter cells. And the fact that DNA has two strands really explains why cells divide in two. And the whole process is very nicely coordinated. And there are three very important switches in that process, points of no return. They are getting into mitosis, getting out of mitosis, and starting DNA replication. And they all have very similar characteristics, namely that the decision to initiate these processes is taken very carefully. But once you've committed to any of them, you can't go back. You can only go on. So that too was a very interesting conundrum. How could you make these irreversible switches out of systems of enzymes and substrates? And it's taken, I suppose, from about, we should say, 1988 to the present date, and we're still not quite, haven't quite solved all the details yet. But there was a very exciting period in time when what had previously seemed deeply mysterious started to get worked out because people could see the outlines. And the outlines really came originally from two kinds of research. One was, as I've described, these biochemical studies on frog egg extracts, and the other was from yeast genetics. And Lee Hartwell, pictured here, was really the hero, and he discovered that there were mutations which blocked cell cycle transition, which blocked these switches from flipping. And but because he was such a pioneer, he could never figure out how these genes actually worked, what they were, because they didn't look like anything else. But he worked out the logic of the cycle. And then, following in his footsteps, Paul Nurse, using a different kind of a yeast, made very important discoveries, focusing his attention on a gene called CDC2. And the reason why he focused on CDC2 was because it was a gene which, if you knocked it out, these yeast could not divide. They could grow, but they couldn't divide. And there was one particular mutation in this gene which didn't knock out activity, but made it more active, so that it actually accelerated cell division. And then it turned out that this gene, CDC2, was the same as one of Hartwell's genes called CDC28. And mysteriously, CDC28 didn't affect entry into mitosis. It affected entry into S phase. So that was very peculiar and caused some confusion at the time. And then Nurse discovered that not only did yeast have these genes, but humans had these genes. And so we realized that studying yeast genetics was a good way of getting at underlying problems of how human cells worked too. But these yeast genetic experiments didn't tell you, nowhere revealed about disappearing proteins like cyclin, because yeast genetics just tells you the components. It doesn't tell you how the components work. And so it was some time before we figured out the relationship between CDC2, CDC28, and cyclins, and it turned out to be a very intimate one. So going back to frog egg extracts, it turned out just as you can lyse reticulocytes and have an active protein synthesis system, you can break open frog oocytes and have an amazing system which is capable of catalyzing cell division, although there are no cells anymore. And this rich, concentrated cytoplasmic extract, which you make simply by spinning these eggs, if you add nuclei to them, they form these beautiful meiotic spindles with purple chromosomes lined up between two spindle poles. And using this system, Jim Mahler and Fred Locher were able to purify MPF, and to cut a long story short, it turned out that MPF was a complex of two proteins, CDC2 and cyclin B, our protein. So suddenly all was revealed, and the two together make once again a protein kinase, and then that suddenly became obvious how cell cycles were controlled. You activate a protein kinase, the protein kinase phosphorylates proteins in the cell, that causes their activity to change, so you bring about all these amazing things like the breakdown of the nuclear envelope and the assembly of the mitotic spindle, the condensation of chromosomes, and so forth. Many of these details still remain to be worked out. So what had previously seemed utterly mysterious suddenly turned out to be very simple, that the cell makes cyclin, the cyclin combines with the CDC2 is activated, it phosphorylates proteins, you enter mitosis, and then the cyclin is degraded, which turns off the CDC2, and you exit mitosis. Well, that was okay for a while, but obviously you'd really like to know how many proteins get phosphorylated by how much in order to bring about these changes in the cell's properties. And this sort of brings about an interesting conundrum, because if you imagine a cell that's not dividing, it's in interphase, and then it starts to divide. You phosphorylate lots of protein. To get back to where you were, all those phosphates have to come off, so there must be enzymes that remove the phosphates. And for a while it was really rather controversial about who did that, and there was no evidence that these things were regulated. And moreover, just to confuse matters further, the geneticists all said that protein phosphatase 1 was involved, and the biochemists all said that protein phosphatase 2 was the important enzyme. And I can remember sort of fights at meetings when saying, you know, and it was most unedifying. Of course, the real answer is that both are required, and genetics tend to focus on PP1, whereas biochemistry tends to focus on PP2. And I began to get very interested in this. In fact, I was once asked to give a talk at a protein phosphatase meeting, and I said that I thought that probably phosphatases must be regulated in mitosis, because otherwise you couldn't completely phosphorylate things when you needed to phosphorylate them. And this was a thing that goes back to very simple biochemistry, namely the existence of things called futile cycles. If you have a process which sticks a phosphate onto one protein and an enzyme that removes that phosphate, it's obvious that you can't fully phosphorylate that protein if both enzymes are active at the same time. You would think there ought to be a control. If you want to fully phosphorylate things, you need to shut off the phosphatases, and if you want to fully dephosphorylate them, you need to shut off the kinases, and there needs to be a reciprocal relationship between the two. I mean, it's very obvious. It's just like filling a sink with water. You have to turn on the tap, of course, to fill a sink with water, but in order to actually fill the sink, you have to put the plug in, because if you don't put the plug in, the water just flows out through the plug hole. And if you think of the tap as the kinase and the plug hole as the plug as the phosphatase, that's exactly how to think about it. And the key person here who joined my lab late in life was a Japanese called Satoru Mochida. And between us we had a very happy, again, collaboration, and we discovered that indeed there is a phosphatase which is regulated, and this is the sort of thinking behind this is shown on this slide here. I mean, we know the kinase is regulated, but is the phosphatase regulated? And the answer is yes, it is. And again, to cut a long story short, it turned out that the regulation of the phosphatase is almost as complicated as the regulation of the kinase, and it's very important. And if you don't, it involves an enzyme called Great Wall kinase, another protein kinase. So I think the message is that protein kinases are tremendously important in regulating cellular processes. And I won't go into all the details, it's complicated. And the other interesting thing about this is that this is a relatively simple diagram, and I learned an awful lot from a friend called Bela Novak, who analyzes these things in quantitative detail and builds models of how these control systems actually work. And together with Satoru, he was able to really get a very accurate quantitative model of how these kinases and phosphatases are mutually regulated. And it's a good example, I think, of how you actually do need mathematical, careful analysis and based on quantitative data to figure all these things out. So, and I really can't emphasize too strongly how important it is to have people you like working with, and how important it is to keep your eyes open and think about things which you're not necessarily working on at the time in order to make progress. Because the nature of scientific discovery is, of course, you discover unexpected things. I think people are apt to think that scientific discovery is something like building a bridge. The principles are already known already, and it's just a matter of just working out how many girders you need and how many nuts and bolts and things, and you just put them together. But it isn't like that. In biology, there are still a lot of things we really do not understand. I think I was lucky to be born when I was, in a period when we really understood so little, so that almost any stone you turned over had something interesting underneath it when you looked closely. But it still remains the case that I think the road may look straight immediately after where you are now, but over the crest of the hill it might turn to the left or to the right or peter out. And it's your job just to keep putting one foot in front of the other and keep going, just to follow the road wherever it leads. Thanks very much for listening. Hi, my name is Tim Hunt, and it's a great pleasure and an honor to be invited to participate in this year's STS Forum. I'm sorry we shan't be meeting in person. I'm not that keen on these Zoomy things, but never mind. This is an important and difficult topic, and I should declare my interest. I'm a basic researcher. I've always been a basic researcher, and my experience of policy and also commercial things is very limited. Although I sat with my friend Jean-Pierre Bourguignon on the ERC Council, so I got some inklings of things from that. But I'd like to talk about something I really do know about, which is messenger RNA, because I worked on messenger RNA one way and another for quite a long part of my career. And as we all know, the most successful vaccines against COVID-19 have been based on the administration of messenger RNA into people's arms. And the interesting thing about this is that it has really been based on about 50 years of basic research, through a spell when people would have said quite reasonably that this was a ridiculous, impossible idea. So the central dogma of molecular biology says that DNA makes RNA, makes protein, and it's proteins that raise immune responses for the most part. So in principle, you can fool the immune system into thinking that it's seen a virus simply by presenting viral proteins to the immune system. And those viral proteins could, in principle, be presented to made in cells such that they would be indistinguishable from the real thing. But there were innumerable difficulties along the line. I suppose the two most important difficulties were getting the messenger RNA into the cells, because messenger RNA doesn't normally cross the plasma membrane cell barrier that's necessary to get into the cytoplasm of the recipient cell. And second of all, the discovery that messenger RNA, foreign messenger RNA coming in from the outside, provokes an extreme immune response of its own, such that it generally causes cells to die. And these two completely impossible things, the second is really the most important one, and as you know, this was really the work of a Hungarian woman who had a very hard time persuading people that messenger RNA would ever be useful as a vaccine, and an American colleague. And between the two of them, did a brilliant piece of work, which they discovered how to get around that problem. And as for getting the messenger RNA into the cells, that became possible by mixing the messenger RNA with a lipid. But the original lipids were so firmly attached to the messenger RNA that it was very difficult for the messenger RNA to get out of its lipid coat once it got inside the cell. So there's been a tremendous amount of development work there And goodness only knows, I mean, probably hundreds, maybe thousands of people were involved in various elements of the basic research. There are another couple of really important things about the messenger RNA. The start of the messenger RNA and the finish of the messenger RNA are also very important and not trivial to get right. So this was something which, had you said, we want to make a messenger RNA vaccine and we need it now, it would have been completely impossible. When I started working on messenger RNA, this business about the immune response was really not understood at all. So there's been a tremendous confluence of research from many, many different angles, from the immunologists, from the basic molecular biology to the practical business of actually making huge production lines for these things, which I don't understand about at all. But I think it is a wonderful example of how basic research has really come to save millions of lives in the last couple of years. I think another very good example of this kind of thing is the GPS system, which we all rely on, which really came out of the very most basic research into the theoretical atomic and subatomic physics in the 1940s, given a tremendous boost by the Gulf War and the military necessity of finding where you were in the desert, to something that you can now carry with you on your phone every day. And I don't really know where the right balance lies between the kind of research that I'm familiar with, which is basic curiosity-driven research, and policymakers, the government funders, the commercial aspects. So I think we're going to have a very interesting discussion on Monday afternoon. Thanks very much.
Thank you very much, Professor Tim Hunt, for sending us the video regarding the message you have learned through your life in science, and also dealing with the questions that all the students might be curious to know. So once again, thank you very much for understanding that he was not able to join us live, but has sent a video and has dealt the questions in beforehand. Well, this is all the lectures that are prepared today for day one. And as we are to end day one, we will briefly go through the programs of day two. If you can see through the slides, yes, tomorrow we will be beginning our schedule at 9 a.m. Korean Standard Time. Will be with us until, of course, the 5:30 p.m. Korean Standard Time. And we have lectures, of course, lecture 4, lecture 5, and the first panel discussion, as well as lecture number 6. So make sure that you be logging in before time. So I kindly ask all the participants who are joining us through the Zoom to log in until 8:55, maximum 8:55 a.m. Korean Standard Time. And with that, now I'm going to let the group into their groups in order to prepare for the poster session. So you can freely move your seats and now prepare for the poster session. Thank you very much.